Okay. Now, well, I thought I hit it, but nothing happened, did it? Yesterday, I guess it was, I did hit it. I'm sure I did. Nothing happened. When I went back and got close to it, I heard it was going, and it's almost a new projector. I went, oh no. The fan was making noise, but it seems to be better now. Slow coming on, but it's better. All right. Any questions for anything we've covered so far? Yes.
I have a question.
Okay.
How do you say it measure the moon? I seen the moon last night in the star.
Yeah. It was a pretty moon too, wasn't it? Yeah.
It was a little star to the right of it, but
Okay.
I'm not a measure.
Okay. Now, there's always going to be a little star somewhere close to it. You need to get a pattern of stars that you can recognize night after night after night. So, did you see a little star in a pattern?
One little star sitting to the right of it.
And no other stars that you can. Yeah.
I seen it that way.
Yeah.
I seen the star to the right of it.
Okay.
But I didn't see a pattern.
No pattern. Okay. Well, try to look for a pattern. Now, I know inside a city you can't see that many stars, but try to pick out a pattern of stars. And last night was a little cloudy as well, so probably the stars were being hid. But boy, the moon was beautiful. That was close to the full moon, wasn't it? It was a full moon.
We have to do this observation at night. Can we do that in the morning?
Okay, yeah, okay, right. Anytime that you can see the moon, okay, and stars. So after the sun comes up, you can't see any stars. But if you get up in the morning before the sun comes up and can see it then, fantastic. Be sure you just do that same time every time.
Yeah, you're asking us to kind of look at it at the same time every day.
Yeah, yeah.
Or every time.
Yeah, every time you see it. Okay.
So we got to figure out the name of the stars.
No, you don't have to figure out the name of the star. It's just the pattern. You know, if this is a group of 3 stars that look like a triangle or a little W or the Big Dipper or, you know, some sort of pattern that you can recognize night after night after night, then once you get that, then what I would suggest is take a clear ruler or yardstick or anything like this, hold it up at arm's length and see how far it is between the moon and that whatever star or group of stars you're going to do from, and then just make an estimation. You can call it 3 inches or 7 inches or whatever it is. That's how far it is. And the stars are lower right, say, or upper, wherever it is from that, you know. And then 2 nights later, or whenever you observe next, how is it compared to that? It will have moved, okay? And that's what you need to note. Is it moving away from the stars, toward the stars, left to right? Left to right of the stars, up or down from the stars. That's the best way to describe it, okay? And if you can throw a direction in there other than left and right, north or south, east, west, but, you know, if nothing else, left or right. Huh?
The way I was standing is,
Yeah.
I guess.
Yeah.
That way.
Yeah. Yeah. When I stood in my backyard and was looking at the moon, it was pretty much to the southeast, is what I would have said, because.
Yeah, it was kind of.
Huh?
I'm sort of in a half valley, so
Yeah.
the sun had set already, which I could see, but I couldn't see the moon until around 8 o'clock.
Okay. Yeah.
About 7:45.
Yeah.
It was still a really bright orange
Yeah.
color, kind of
Yeah.
low. It was nice.
Right. That's not bad. Okay. All right. And this is Chelsea came in. Has anyone else come in since I called roll? Okay. All right. Those were a couple questions on the lab that you're still doing. Now remember, in class, we did the vast majority of the lab. So don't, just because you may not feel like you're getting adequate measurements or stuff like this, don't throw this lab out, because we've done most of it already. So try to carry it through and get it done. All right. So let's talk about where we are and what we're going to do then. We're in chapter 17. We just sort of got started on it last time, So I'm guessing probably we're not going to be quite through with it today in time for a lab, but if we do, we can get that done. But the last 30 minutes today is going to be your test on Chapter 16. So hopefully you have your formula and equation sheet. If you don't, you can be working on that now while we're having class 2. Try not to miss too much of class either. All right, any questions before we get going?
You said the formula equation sheet?
Yeah, anything you want to write on a piece of paper for the Chapter 16 test. That'll be the last 2 hours, last 30 minutes today. All right, now, and for those who came in late, I still haven't heard back from the guy at Sanford. And it seemed like this summer it was the same thing. I had to call him 2 or 3 times, and finally when I finally go, oh yeah, I've been meaning to return your call. Okay. So we were several days late this summer. Most years I've been able to catch them within 1 or 2 phone calls. Summer was tough though, it seemed like. I don't know about fall. Of course, yeah. By the time I get out of class, it's late in the day and he's usually gone, and I have to catch him over lunch hour, and then he's usually at lunch. So I think that's the issue. Although I'm in class all morning, I'm in class all afternoon. All right, let's look at some crystal structures. The illustration we saw, if there's no more questions, illustration we saw several things ago. Whoa, I thought we had already seen that. There, that crystal structure. That was sodium chloride, halite. What kind of structure did we call that? Cubic structure. It was an isometric structure, cubic. Okay? And then when we classified the crystal structures, there was an example of the cubic structure. Well, this is a micrograph. I don't know if it's an electron microscope or not, but these are indeed little salt crystals. And what do they look like? Little cubes. That is your salt crystals. The structural unit for the crystal of table salt, sodium chloride, is cubic. And you can see most of those are pretty close to perfect little cubes. That's how they form. Okay? Now, next to that, now in your text you don't have this figure anymore. You just have showing on top of a salt shaker, and there you can almost pick out that they're little cubes. Okay? But then figure 17.5, the one on the right there, is a quartz crystal. Okay? Kara? Yeah. Trying to find you on the roll. Okay. And that's a quartz crystal. Now that's a big, pretty quartz crystal, okay? And it's sort of hard to tell because it's a three-dimensional thing, two-dimensional picture, but you can almost tell, I'm pretty sure this is one of those hexagonal structures. Not perfect by any means, but if you go back, see that prism, the hexagonal structure, upper right, the one to the left there, that's pretty close. It kind of looks like the prism on the tetragonal structure, but it seems like it has more, it has the points on the end, but it seems like it has more sides than that. But anyway, you can tell that regular shape, that's the crystal structure. Here's a face, there's a face over there. Here's, you can see these here. And when we do the lab for this chapter, while you're doing that, I will be passing around samples, and you can see some other quartz crystals pretty nicely in some of the rocks that people have either brought me or I've found over the years. Okay? Those are your crystal structures. All right. Now, the next subtopic, also on page 439, is talking about two types. Well, let me back up a little bit more. Remember when we talked about the earth materials? What are the two most common materials elements on the Earth's surface, in the Earth's crust? Oxygen and silicon. Okay? Well, guess what? When you put oxygen and silicon together, they form what they call a silicate. SiO4, I believe it is. So 1 silicon, 4 oxygen. That's almost the ratio you have there. That looks more like a 1 to 2, but you see silicon's heavier than oxygen, so it's more like that. So it's not surprising that the silicates, which have oxygen and silicon in them, make up the predominance of what you have on the surface of the Earth. So, silicates contain mostly silicon and oxygen, with some other things too, depending on if it's a sodium silicate, an iron silicate, whatever kind of silicate it is. But silicates, the classification of silicates, makes up 92% of the Earth's crust. Everything that's not silicates is only 8% of the Earth's crust. So by far, most of the Earth's crust is made up of silicates. And it's based on, and I think I said it incorrectly before, I said hexagonal. It is the tetragonal unit, and that's what you're seeing there, that tetragonal unit. And going back, oops, there it was right there, the tetragonal unit here. And that, like I said, actually was more what it looked like. That is indeed tetragonals. Well, I don't know. I'll take that back again. I'm not sure on that, but I think they mean here the tetragonal, tetrahedral unit of the silicon in the middle and then 4 oxygens around it. That's what they're talking about, the tetrahedral unit there. Well, let me see. I got to sneeze. Trey? Yeah. Sorry. Y'all awake yet? Okay. May have to go again. Sorry. At home, my wife screams and the dog jumps. It's just crazy. Okay. All right. So it's based on that silicon-oxygen tetrahedral unit with 1 silicon in the middle and 4 oxygens around it. Okay? Now, there's 4 ways that those silicon-oxygen tetrahedral units go together. You can have the isolated tetrahedrons. Now let's go back to the graph and let you see. Here is the tetrahedron. The silicon would be in the middle, and there's 1, 2, 3, 4 oxygens around it. Equally spaced, that's one of your isometric structures. So the individual crystals or individual structure of the tetrahedrons are that. Now they go together in several different ways. First of these is isolated tetrahedrons, okay? Then you have the chain silicates, okay? One tetrahedron will then share a pair of oxygens with the other, with another, and another, and they form a chain. Some of these, and you don't need to know these names, like halloysite would be a lot like kaolinite, only it's a chain. There are others. Your asbestos is a tetrahedral chain. Sometimes pretty bad, but other times not that bad. You just can't tell which are the bad ones and which are not. So there are several of those. Serpentine, there are several of those chain silicates. Then you have others that don't just form one to another and form a chain. They form a sheet. This pair and that pair and this pair, all of them around, that would be your sheet silicates. And then you have the 3-dimensional sheets. They call that the framework silicates. Here are sort of there's your tetrahedral unit, like I was showing you before. The silicon in the middle and then the oxygens around. Now, they do this several times. They did it with the sodium chloride. They did it here. They make all the balls look the same. In reality, the Si is a +4 charge, meaning it is really short. It hasn't really lost 4 electrons, but its electrons are shared elsewhere, so it gets smaller. The oxygens have -2 each, so they have extra electrons, so they get a bigger cloud. So really you have a little silicon in the middle and great big balls of oxygen around that. Okay? That would be more hard. Make these much bigger, and that would be a better illustration of this. Now that's three-dimensional, not two-dimensional. This one is, looking at this, is out front, and these two are over here, and that one's sort of to the back there, but they're equally spaced around that silicon. Okay, so the first up here are the individual isolated tetrahedrons. These right here, the A's here. Okay? The B's are the, things that pollinate. No, these are the chain set silicons. You know? It's not a straight chain, it's sort of a wavy chain, because every two oxygens get shared with, or one oxygen gets shared with another one. So the bond is shared. Number C is the sheet silicates, and I don't like their illustrations here. They just show a few together. But that's also a sheet silicate. So the framework silicates would be a three-dimensional. You get that with them on top of each other. For instance, I mentioned two clays. One was, well, let's go back. Kaolinite clay. That's the kind that you find most often here in the southeast. I don't know if Alabama has any kaolin mines in it. I know Georgia does. There are several, now sometimes they're called the chalk plants or kaolin mines or some things like this. But Georgia produces a fair amount of kaolin. Does anyone think of anything that we use kaolin for? Second? Yeah.
Kaolin to me sounds like kale. I don't know why.
Okay, not the vegetable kale. This is, it's spelled Kaoline, kaolin. Okay? One thing you all use sometime in your life, pencil lead. The dark part of pencil lead is carbon, graphite, sort of like soot. The trouble is that's a real messy thing to try to write with. It smears real badly. So what they do, they combine graphite with kaolin. And that's how you get different hardnesses of lead. A number two pencil lead will be, I don't know, maybe 50-50 kaolin and graphite. But then the harder leads would be more kaolin, less graphite, and the softer leads would be, like number ones, would be more graphite and less kaolin. So that's one place we use kaolin, okay, pencil leads. Another place, anytime you have a glossy thing like this cover, what makes it glossy? They put a layer of kaolin on it. Kaolin is very, very thin. That makes it glossy. Magazines, things like this. They're hard to write on because that kaolin is too slick, okay? So anytime you have glossiness, that's one. Now, of course, another thing, I don't know if any of you are old enough to remember the old remedy for an upset stomach, KO pectate. You know what the KO comes from? Kaolin. It has clays in it. And what clays are things with lots of surface area. Tiny, tiny little particles, lots of surface area. So if you do have that upset stomach, you got some excess acid in your stomach or toxins and things like this, the kaolin absorbs them, and after a while you pass them on out, okay? But that's what kaopectate and probably Pepto-Bismol has some kaolin in it. Just about anything of those cloudy, milky-looking things, you probably have kaolin in that. So for lots of things, that's just one type. But kaolin, as I was going to say, is a framework silicate because it has one layer of silicon oxides, silicates, but then the next layer is going to be aluminum oxides or aluminates. So silicate, aluminate, silicate, aluminate, okay? And that's your framework silicates, okay? They're mixed in with other things. Other types of clays, we don't have that many of in the southeast. However, down in the Black Belt, I don't know if any of you have ever been down there, it's called the Black Belt because the soils are very dark, okay? Very fertile soils, but also very hard to manage soils. And anyone know why I say hard to manage? If they dry out, they crack like crazy. In fact, I had someone in a class many years ago who grew up down there. He said, yes, when it got really dry, the soil would crack so badly you could stick your whole arm down through a crack. It just cracked like crazy. Now, I bet you, if you have any clay in a yard or something like that in the real hot part of summertime, not like this summer when it rained every other day, but when the soil sort of dried out, you'd see little like puzzle cracks, all over. That's from your clays losing waters, losing moisture, and shrinking. Well, down in the Black Belt, when they shrink, and you can get your arm down in those cracks. And that makes it tough for growing crops because where the roots are there, suddenly they get pulled apart when the soil separates like that. So that's why it's so hard to manage soil. But they're very, very fertile soils. Well, those clays are 2-to-1 clays. See, a kaolinite is a 1-to-1. It has a silica alumina, okay, 1-to-1. Those clays that shrink and swell so badly, those are 2-to-1 clays. Silica, alumina, silica, silica, alumina, silica, silica, alumina, silica. So then those two silicas really absorb water in between those layers like that, and they expand like crazy when they wet, and then when they dry out, they shrink, and that's why they crack like they do. Now, another use for that, there's a type of clay called a bentonite. They mined this out in Wyoming and other areas in the Rockies, and the Wyoming bentonite swells so much. What they use that for is when they build an earthen dam, like you're damming up a creek or a river, using earthen dam, not building a concrete dam. Building an earthen dam, and like my father put one on our farm when I was growing up, and actually I was in college, I think, when he built that, or had it built. In the middle of the dam, in the core of the dam, they deposited, he had to buy and they purchased and put it in there, a big layer of Wyoming bentonite. Why? Because when the moisture, water backed up and leaked through the dam, rather than leaking through the dam, it would hit that bentonite clay and it would swell up and basically plug the dam, keeping water from flowing through it. It swelled that much because he put soil all above and around and stuff. So that was sort of the plug for the dam, to make sure the dam didn't leak. And so, yeah, those are your framework silicates. Layers on layers. They're sheet silicates and layers. Okay. Now, let's look at the non-silicates. Guess what? We only talk about 8% of the Earth's crust, but we talk about it because they are, even though it's not nearly as abundant as silicates, they still are significant. Okay, in these you have no silicon-oxygen tetrahedrons in the crystal structure. You have other kinds. These make up the remaining 8% of the Earth's crust, so some of these are in pretty small amounts. 8 groups of non-silicates. The most abundant of the non-silicates, all of the non-silicates is 8%, so still not all that abundant, are your carbonates. Now there's 2 major types of carbonates we have. One is calcium carbonate, and that's largely makes up what we call limestone. And underlying most of Alabama, Georgia is underlain by granite, which we'll talk about later in this chapter, but Alabama is mostly underlain by carbonates. Especially the Black Belt, that's actually really heavily underlain by that, and it's actually a chalk, and that's what makes those really rich, dark soils. But the rest of Alabama still is underlain mostly by carbonates, and so we have quite a few here. They make a pretty fertile soil, and they make pretty heavily clay soil that holds moisture well. So we have a lot of advantages over Georgia. Our soils are typically better because of the parent material, the carbonates. So one of those is calcium carbonate, which is our most common limestone. But there's also another kind of carbonate. It's also a kind of limestone, but it's magnesium carbonate. Calcium and magnesium are right in the same family there in the periodic table, one right above the other one. And that is called a mixture of magnesium and calcium carbonate is called dolomitic limestone. Okay? In other words, dolomite. And there's actually a town a little to the northwest of here named Dolomite. Okay? I'm guessing they have some dolomitic limestone there. Now, dolomitic limestone, okay, now, what do we use limestone for? Well, they use it in buildings and things like this. But agriculturally, we grind it. Say again? Okay, we call it a fertilizer. It's actually a soil amendment would be a better name for it. It's not all that fertile, but what it does for you, good you're thinking that way, it actually reduces acidity. Now, over in Georgia, because they're underlain by granite, that's an acid igneous rock, so their soils are really acid and can get so acid it's hard to grow things well. And so what they do, they lime it with limestone. Yeah.
Do you have flower gardens?
Yeah.
You do them yourself?
We put beds around the house. Yeah.
You take care of them? Did you get out there?
Oh yeah, I love it. Yeah, you do too.
I like to.
Yeah. We have most of ours are more in pots on the patios and stuff like that, but we do have a few that we put in the yard as well, and we have azaleas and that kind. We did all that in our yard.
I just kept thinking of what I heard carbonate, and I remember sodium bicarbonate.
Okay.
Is there a relation?
Okay. See, now sodium carbonate is another that's not usually shown too much in minerals, but you will have it some in some. But what sodium bicarbonate is, and you do much cooking, and you have soda, baking soda, that's sodium bicarbonate. And what it does is when you mix it with water and especially heat it, the sodium bicarbonate releases carbon dioxide, and that's what makes the breads or the cakes and things rise. If you don't have yeast, usually you use soda, baking soda.
It's gassy. Is that like for carbonated drinks?
What's that? And carbonated drinks? I'm guessing that's largely sodium bicarbonate, but I don't know for sure. But yeah, carbonated drink, the bubbles in there are carbon dioxide. Same thing as what helps make the bread rise or the crackers or crabs. Yeah.
I'm kind of an avid soda drinker.
What?
Avid soda drinker.
Okay.
So I can understand like the carbon dioxide and the soda. What happens if you drink so much of it? What does the carbon dioxide do to your system?
Well, carbon dioxide itself really doesn't hurt you in many ways. But if you think about carbon dioxide, CO2, in water, H2O, now you have H2CO3, which is the chemical formula for carbonic acid. So the worst thing it does for you, in my mind, it is a mild acid, not a strong acid. But that's why it has sort of a sharp fizz to it and stuff. But that eats away enamel on your teeth. That's one of the probably worst things that carbonated drinks do for you. Another thing, and we say it's carbonated drinks, but some of them will have, rather than carbonic acid, phosphoric acid. And this is not, it still has the fizz from carbonate, but it also has phosphoric acid as well. And phosphoric acid can start over time leaching away the the calcium out of your bones and lead to osteoporosis. So, and women usually have more of a problem with that than men do, but men do have problems with it some. But so that is the other thing that soft drinks are kind of bad for you. It can lead to osteoporosis, or the weakening of the bones. That's all tied up with estrogen and the estrogen levels and things like this, and especially a woman when she goes into menopause and not producing as much, really it can be quite dramatic then. So it's just something to be careful about. And then the other thing, if they're sugared soft drinks, then you got the issue with sugars too. So a lot of people go with the diet stuff, but still it's not. My sister-in-law, my wife's sister, is a fairly tall woman, but she has scoliosis, which is a curving of the spine. If her spine were straight, she would be probably 6 feet or taller. But it's not. It's sort of curved. But she was a swimmer, so she has good muscle structure. So she holds herself well, and so far hasn't had any problem. But her husband's a dentist, and he's on to her all the time because dentists don't like you because of that. But he said, it's not helping your bone structure any, and as you get older, it's going to give you more and more problems. So he's trying to talk her into doing less carbonated drinks. She's a big Tab lover. Okay, she drinks a lot. Huh? Tab, the old. Yeah. She finds them somewhere. Somebody does make them, but when she does it, she does Diet Coke. But she's a Tab lover many years back. Okay, so there's your carbonates, and what we're talking about limestones. And one reason dolomitic limestone is better than calcium limestone, which is what we call limestone. The dolomitic limestone has magnesium carbonate and calcium carbonate. Well, generally, there's plenty of calcium. I mean, plants need calcium, but there's plenty of it available. But plants also need magnesium, big time. What would you say one of the most important cells, I would guess you say, in the human body? Think bloodstream. What's a really important thing for us to have in our bloodstream?
Platelets, white blood.
All those are important. Red blood cells, is someone saying? What makes red blood cells red? We call it hemoglobin.
Yeah.
Hemoglobin, right? Now, when you see hema, think iron. It's Fe, which is ferrous and stuff like this, but one is Greek and one's Latin, I think. But when you see hemoglobin, what hemoglobin is an iron atom or ion in the middle with a carbon kind of structure around it, a claw holding it in place, basically. And that's one of the most important things for us as humans and animals, because that iron picks up oxygen and carries it to the various parts. That's what hemoglobin does, carries it to the body for you to oxidize and do whatever you're going to do, and then returns. The iron's still there, but it's lost oxygen. So the iron is the oxygen carrier. One of the most important cells in the body, hemoglobin. Now, why did I get off onto that? In those little green leaves out there of every green plant, you have a structure that's almost identical to hemoglobin, except it's not iron. It's magnesium. And that chlorophyll, cell of chlorophyll, that what does chlorophyll do for the plant? It pulls the carbon dioxide out of the air and uses that carbon dioxide to build structure, wood, things like this, and it's the thing that pulls sunlight. Okay, two things. Sorry, back off of that. What the carbon dioxide does, that builds the plant, but what the chlorophyll does is that provides the energy for doing that transfer. It takes the light from the sun and converts it into chemical energy that's stored as a sugar bond. You mix carbon dioxide with water, and you get H's and C's and O's. Well, the simple sugar is H12, H6C, H12C6O12 or something like that. It's the simple sugar. And that's made from the H and the O's are from water and C and the O's from carbon dioxide. Okay, and that's how they're formed. The chlorophyll is what takes the energy from the sun and converts it to storing it in the chemical energy of that sugar. Then later we eat the sugars of the starches and stuff, and that's what gives us energy. Thank you, plants. If it weren't for the magnesium in there, so if you do have to line your plants in your yard, like in your garden or something, and most of the time in Alabama we don't need to do much because we've got a lot of limestone in the soil. But if your soil is pretty acidy, like if you're near an old mine or something, that can be very acidy. And talking about acid, no, I'm sorry, here's 100. Okay, is here. If you have a soil that's really acid and you do lime on it, the cheap lime is calcium carbonate. A little more expensive is dolomitic limestone, which has calcium and magnesium. Better to go with that. That provides the chlorophyll, the magnesium you need for chlorophyll. Now, disadvantage of it is slower to dissolve, so it doesn't cut down the acidity as rapidly, but it will do it over time. Now, a time out here, and I know this is a horticulture class, if you do have azaleas in your yard, or rhododendron, or camellias, or a lot of these really popular southern plants, don't ever line them. What's that? Okay, what actually happens is they were developed, they were produced, they love the acid soil of the South. So when you put too much lime on them, they can't handle it. They need the iron from the soil, and the iron gets less available when you put limestone on it. So they want that iron. So don't ever do that. We did have a guy, a friend of mine, used to work here at the college, come and do some of our front yard stuff. We just didn't have time to do it ourselves. And some of the workers that he had working for him, they did several things. They did a little walk for us and stuff like that. So they had used finely ground limestone in that for the mortar and other things like this. And then they put out all these camellias. Okay, not a whole lot, but several. And they just started dying like crazy. We watered and watered, and we couldn't keep them alive. And when I dug up the first one to replace it, we found some others and we're going to replace it. I dug it up there, under there was all this finely ground limestone that he had used. Well, didn't use it all. Let's put it in the yard here, and tried to plant the plant on top of it. And it wasn't the guy that I knew. It was a worker under him, and he hadn't been there that day. And he did it, killed every one of them. I think we have 2 or 3 left because, well, this looks like good stuff. It almost looks like fertilizer. Let's put it underneath, and they died because they couldn't get the iron they needed. So those are your carbonates, way more than you needed to know about carbonates. Another kind of non-silicate is your sulfates. Carbonates are carbon oxygen. Anytime you see the 8, that's oxygen. Silicon oxide, carbon oxides. Sulfur oxide. They're not oxides, they're carbonate. But silicon with oxygen, carbon with oxygen, sulfur with oxygen. Now, 2 of the main sulfates that we have, most common, one is calcium sulfate. And that has a name. We don't have any sheetrock in this room. That's not quite sheetrock. But what do we often call sheetrock? There's another name for it. Something board. Huh?
Drywall.
Drywall or blank board.
Drywall.
Okay, drywall. Maybe you ever heard it called gypsum board? Gypsum board. Gypsum is calcium sulfate. Okay? And what that is, if you ever look at the, basically drywalls, sheetrock, gypsum board is a sandwich. Paper here, and then in between is the gypsum. Now, it's not pure gypsum, but it is. But it's just sort of a gray type thing that's mostly calcium sulfate. Now, agriculturally, we also, farmers down around Elba, is that it, the town in southeast Alabama? And in that area there, they grow a lot of peanuts. Peanuts, does anyone know a plant that peanut is closely related to? Probably don't think of them in the same thing, but they are. Yes?
I'm afraid to say it. Cotton?
No, not really cotton. It sort of looks like cotton, but it's more like soybeans or any of your legumes. Okay, peanut is a legume. Yeah.
I said cotton because I remember George Washington Carver, he found ways to use peanut oil and cotton. So
Yeah.
I thought they were associated.
He did more with peanuts, I think, than anyone else ever has. I mean, peanuts are a good crop now because of him. Probably largely because of him. Now, finally, people are making almond butter as well as peanut butter, and I've even heard of cashew butter. But he invented, I think, peanut butter. Great product, one of my favorites. Okay, but peanuts are like your other legumes, like soybeans or peas or something, most like soybeans. So actually, they bloom. But then when they bloom, because in the soybean, the bean pod forms above ground, like any beans and peas. But what a peanut does, it blooms above ground, it gets pollinated all like this, and then it has to peg and go underneath ground, and that's where the bean pod grows, which we call the peanut. Okay? It's just like a soybean pod, only a little different. Okay? And but it has to what they call peg. Well, peanuts won't peg unless they have enough sulfur in it. Enough calcium in the soil. Okay? Now, and the soils in Alabama and Georgia where they grow a lot of peanuts usually are overflowing with calcium. Okay? But if you add limestone, which is calcium carbonate, you raise the pH. Well, peanuts require a low pH. You want them more acid. They're a good southern plant. So in order to add calcium but not change the pH of the soil, you use calcium sulfate. And the peanut farmers, if you hear them, they won't call it gypsum. They'll call it land plaster. Oh, I put out some land plaster. That's gypsum. Just like the plaster you put on the wall, this is gypsum board. Okay, gypsum. There is another sulfate, just like with calcium. You have, with carbonates, you have calcium carbonates and magnesium carbonates. Same thing with sulfate. Calcium sulfate is gypsum. Does anyone know what magnesium sulfate is? And again, for you plant growers, you probably run into it. Or people who might have problems with aching feet. What was the old remedy? What did people soak their feet in? Second, Epsom salt. Very good. Okay, Epsom salt, that's magnesium sulfate. And what you also use Epsom salts for a lot is your ferns. If you have potted ferns and things like this, and they're beginning not to do so well, put not a whole lot, but just a little bit of Epsom salt solution in them. They'll usually perk right back up. Okay? My grandmother had heard you did that with African violets as well, that they could use a little dose every now and then of Epsom salts. And she also had gout occasionally, so she soaked her foot, unfortunately in pretty concentrated Epsom salts. And then she was very thrifty, good German, so she poured that on her African violet, but it was way too strong, and she had the most beautiful African violets, and she killed a bunch of them. Stop putting too much Epsom salt on. Okay, but that's another story. Those are your sulfates. Then you have your oxides. Can anyone think of any oxides? Okay, now peroxide is very similar to oxide, but a little bit different. How about iron oxide? Anyone know what that is? Yes, you do. You just don't know it by that name. Rust. Okay? Iron oxide is rust. Okay? And what color is rust generally? Reddish. Okay? Now, let's go back to our bloodstream here, the hemoglobin. Is all your blood red? No. What's the other color? White? Blue. Okay? Your veins are blue. What are veins doing? Returning the used blood to your lungs. When they go to your lungs, the blood turns red again. That's because the iron in the hemoglobin has two valence states. Okay? There's a +2 and a +3. The +2 is the reduced state, +3 is the oxidized state. And when you have the blue blood, the venal blood, the vein, that is FeO, ferrous oxide. Your iron has lost an oxygen. And it goes back to the lungs, it picks up another one, becomes ferric oxide. Okay, ferric, which is red. Okay, so your arterial blood is red and your venal blood is blue. You see more of the venal blood here because it's not as crucial. If you were to nick the vein, you could bleed and stuff like this, but you don't want to nick the artery, because it's under more pressure from the heart. It's being pumped to the thing, and that's also the blood that has the oxygen that your muscles need to keep doing. So you don't want to lose that. So that's that. Now, the hill right next to the house where I grew up mostly, we moved there when I was in the 6th grade, and my sister still lives in the house. The field right next to the house over in Georgia, red clay hill. I mean, just bright red clay when you tilled it and stuff. But at the bottom of that hill, it was grayish, darkish kind of soil. And I just thought, well, all the topsoil eroded off the hill and went down there in the bottom. But I found out that wasn't the case. That was the same clay that you had up here. It was down here. But you see down at the bottom, it was sort of a swampy area where a lot of moisture would be there. That iron got reduced and went to the grayish, bluish look. And on the hillside, it was very well oxidized, so that was the red clay. It was the same iron in both. This was ferric oxide, that was ferrous. So that's one type of oxide. You also have aluminum oxide. Just about anything will combine with oxygen. Oxygen combines with just about everything. Now, you mentioned peroxide. Let's take water. Water is hydrogen oxide, H2O, hydrogen oxide, okay? What hydrogen peroxide is H2O2. Oxygen forms a peroxide, what they call radical, and it acts a lot like a single oxygen, only it's a peroxide. And we use that sometimes for disinfectant and things like this. It'll actually bubble up on a thing that's infected, and that is, the oxygen is being released and oxidizing the germs and then the other things you don't want, and that's what makes it antiseptic. Okay. So lots of things can be oxides. Okay? Sulfides. Well, that's what oxide, what an 8 is something like calcium carbonate. The carbon and the oxygen are combined together, they combine with the calcium. Magnesium carbonate. Carbon and oxygen are bound together, they combine with magnesium. Okay. Sulfate is sulfur and oxygen combined together, combined with oxygen, with calcium or with magnesium or whatever. Oxides are just something combined with iron. Iron oxide, aluminum oxide, some of you guys may be more familiar with this than the gals. Do you know what zinc oxide is? Have you ever, okay, most of our nails and things like this are iron, aren't they? And if you're going to be in an environment where the iron may rust, and you don't want it rusting, what kind of nail do they sometimes use? It's a nail that sort of has a coating. Say again? Galvanized nail. What a galvanized nail is one that has zinc oxide coating on it. And that zinc oxide will then keep the oxygen from getting to the iron and rusting. And not only that, keeps the moisture away too. Okay? And so zinc oxide is a galvanized nail. Now, going back to an agricultural application of that, if you have pecan trees and your pecans start having too many of those dark, bitter spots on the meat, ugh, pecans, I love pecans. Boy, you get one of those and you just want to spit it out. That's probably because it has a zinc deficiency. And one of the simplest things you can do is take a galvanized nail and nail it into the tree. Yeah, and that will release enough zinc from the zinc oxide. The xylem and the phloem, will take that up and will sometimes remedy that really, really easily. You could put zinc around the tree and stuff like that, but that may take a while nailing it into the tree. Now, the disadvantage of that is when that tree ultimately dies and someone comes there with a chainsaw and saw it up and they hit that nail, they will not like you for nailing that into the tree because you probably just broke your chain on the chainsaw, but never mind. Were you going to say something else? I thought you were.
Yeah, I was going to say, why do people take lime and paint those trees? The bottom of the tree, white. You seen that, how they mix that lime up and then paint the bottom of the trees.
And paint the bottom of the tree?
The tree be white. You ever seen
I
that?
think I have.
Like you ever see people cut trees down, and it's just a stump down instead of ground stump up, like this lime stump. But they don't want to grow it.
Oh, okay. I didn't know that's why they did. Now, sometimes, like on the farm, when my father would have them come in and cut timber and stuff like this, he would go in and paint the tree that he wanted them to cut. He'd paint the tree pretty obvious that they could see, but then also paint the stump. And the reason he did that, if he came in and saw a stump that he hadn't painted, he didn't want that tree cut. And they had got that tree and hauled it out too. Where they had only paid him for the ones he painted, they took some extra. And, So I knew he did that for that reason. And sometimes use lime or something else, sometimes just paint. But he used to use a mixture like that too. But yeah, sometimes if you clog up the vascular system of the tree, yeah, it'll keep it from growing. Now, I bet you that's why they do it, but I don't know that for sure, I'm guessing. Okay, so those are your oxides. Well, then the sulfides are when you have just something combined with sulfur. Okay? Now, some of the common ones of those is iron sulfide. Now, that has a special name, iron sulfide. Anyone know what it is? It's called pyrite. Pyrite has another name, because pyrite doesn't look either red or dark or gray or anything like iron, and the sulfur is yellowish, but when you combine the iron and the sulfur together, it forms a gold kind of color. Fool's gold, that's what pyrite is, iron sulfide. And so if you ever see any of that, you've got that. A lot of times your sulfides will come to the surface when they do deep earth mining, probably even the coal mines, but certainly things that go much deeper. When you bring that soil up, it's been not oxidized for a long time, bring it up and then it starts oxidizing, that acidifies like crazy. And that's why I said if your home or something is former mine spoil, where they mined many years ago and now sold the land and people build houses there, sometimes even though we're underlain by limestone, your soils may be very, very acid. And that's when you do want the lime. because you need to drop that acidity. That's from the sulfides we bring from very, very deep up to the surface. The halides, we already ran into one. Sodium chloride is a halide, but it's just one of many. Where the HAl comes from is this, not the 8th column here on your periodic table. Those are your noble gases. They don't react with anything. They have a completely filled outer electron shell. They don't share electrons. They don't gain or lose electrons. They're happy. Those never form compounds. They're always pure elements. Okay, but the 7th column, they're missing one electron to be full. They want that one, so they grab electrons wherever they can, and those are called the halogens. And those are your fluorides, your chlorides, like table salt, sodium chloride, bromides, iodides, usually don't have it much below that, but those are your halides. So therefore, yeah, your chlorides, all of those are your halides. Now that last column is called the halogens. That 7th column is called the halogens. Now, in some languages, that just means salts. Yes?
What would it be under if sulfates or sulfides? Which would what is it's not hydrogen chloride, but it's something that burns if it gets on your skin.
Yeah. Any of your acids will do that, including sulfuric acid.
Sulfuric
acid is a sulfate, hydrogen sulfate, one of the strongest acids going. Anyone know where we use those every day? Though you don't touch them, hopefully. Your car batteries. Those are called lead acid batteries. So you have lead in there, and you have sulfuric acid in there. Okay? So there is a name for sulfuric acid that I can't think of it. It's an old common name for it, and I cannot think of it, but it was really, really strong acid. They use sulfuric acid in producing papers. You use it for there are many other things that sulfuric acid is used for, but it tears things down really badly, including skin. If you ever splatter that on your shirt, you can wear that shirt on Sunday because it's going to be a holy shirt. Okay. But yeah, your sulfuric acid is very strong. Now, hydrogen sulfide is also a weaker acid. That's called hydrosulfic acid or something like that. But I bet you, if you've ever encountered hydrogen sulfide, you recognized it. You may not know what it is. You know the rotten egg smell? Hydrogen sulfide. Yes?
And isn't that also with propane too?
Actually, they put that smell in the propane. See, natural gas and other things like this sometimes are odorless. So if you have a gas leak, you don't know it. So they put a strong odor in it, like hydrogen sulfide or something like that, so that when it does leak, you know. Okay, so that's something added as a safety feature. I think. I believe that's what it was.
So you mentioned egg.
Yeah.
You know, you take eggshells and you put them in water and you talk about that smell, and it makes fertilizer.
Yeah. The eggshell. We compost everything we can compost, and they say.
It smells bad.
Yeah, and that's mostly because of the egg residue that's probably on it, because eggs are very rich in protein, and so any of that, when it starts decaying, you get the hydrogen, because the proteins quite often, especially egg proteins, have sulfur in them. That yolk is, the reason it's yellow is the sulfur, but all of it has some sulfur, so when it decays and becomes hydrogen sulfide, you know it.
Yeah.
But the only animal product we put in our compost is eggshell, and it's a pretty good, when it breaks down completely, it's a pretty good fertilizer, but it stinks. Okay, you got that right. Then we have the phosphates, and again, this is phosphorus combined with oxygen. Okay, Now, phosphates, again, I like you gardening people. When you buy fertilizer, quite often the bags of fertilizer will have 3 numbers on them. You know what the 3 numbers stand for? Have you ever seen, you know what I'm talking about? 5, 10, 10, 5, 10, 15, 10, 8, 12, something like that. The first number is your nitrogen, okay? And nitrogen is one of the most important fertilizer elements you got, because all proteins have nitrogen, okay? Got to have that, okay? The other 2 are potassium and phosphorus, actually phosphates. And I always forget. I think it's phosphorus and then potassium, but it may be vice versa. They start with P. I can't remember which is which. Huh?
You had it right the first time.
Which?
Where it was saying
Phosphorus and potassium. I think, yeah, that's what I thought it was. Okay? So the phosphates are an essential plant nutrient, and here's where they are used. And again, it's that energy, the thing that most important things those plants do is take energy from the sun and convert it to energy to build chemical bonds, your sugars, okay? And how they do that is ATP and ADP. Have you ever heard those? Adenosine triphosphate, adenosine diphosphate, ADP and ATP. And when it goes back and forth the other, that's how the energy is transferred, okay? And it's part of the complex reactions that go on in those little green leaves all the time. They're out there working. They're making those things happen. So the phosphates are really important to plants, but phosphates are also very difficult to keep soluble. You can't dissolve them in water very easily because they're a pretty complex thing. So you have to always add a lot more phosphate fertilizer than the plant will ever take up. So the main mineral for that is called apatite. Now, it's not like I'm hungry apatite. It's A-P-A-T-I-T-E, not A-P-E-T-I-T-E. But apatite. They do a lot of phosphate mining in central Florida. Lakeland, Bartow, that's Polk County. And my wife was just telling me last night and the night before, some sheriff or somebody in Polk County has really come down obnoxiously hard on. Oh, yeah, I remember what it is now. They're expecting the Hurricane Irma to come through and probably cause. So a lot of people are going to be going into shelter. So he's taking the opportunity to arrest as many people as he can. Supposedly, people with outstanding, warrants and things like this. But the fear is he's going to be targeting undocumented folks. So I find that totally obnoxious. But anyway, they do a lot of phosphate mining there. The trouble is we have already mined most of the easy to access phosphates. Okay? And without phosphate fertilizers, we can't grow all the food that we need. So if we are going to be approaching a tough situation, that's probably going to be from lack of available phosphate fertilizers. Yes?
Actually, on that topic, I believe that we'll run out of different food groups before we run out of phosphates and iron and all the minerals that we got in the earth. We'll run out of, like, staples, like fish and other things.
Okay, yeah, you're absolutely right there. We are
wild game meat.
Yeah, you're absolutely right there. Especially when you said fish, we have overfished enormous areas of the ocean. I mean, what was the Sargasso Sea? Was it in the north? They used to do halibut fishing or something up there in North Atlanta.
The halibut is nearly extinct. Right?
Yeah, it's almost extinct because we have overfished like crazy. I mean,
Let's go on and do deep sea fishing.
what's that?
Do deep sea fishing.
Okay, the trouble is there's limits on that too. They will not let you catch more than so many red snapper or grouper and stuff because people have overfished it like crazy.
Especially if it's
What's that?
around this time, you can't. If you catch like red snapper around this time, you can't go back.
Oh, yeah, okay, you gotta throw it back. You're absolutely right. Because we have overfished like crazy. So I understand what you're saying there.
So
But-
it should take like if there was a shortage and nobody was really allowed to fish, it would take about maybe 50. I was watching a video about it, but
Yeah.
it would take 50 or more years for the fish population to get back up to what it was.
To what would be, sustainable. So, and the trouble is, I'm not sure that all those fish that people are catching, they're actually consuming. They're just sports fishing. And could be damaging the fish, even though they throw them back, it could have damaged them enough they're not going to live. And think of the buffalo. I mean, they said the herds of buffalo that went through our Midwest back when the settlers first got here, monstrous. And what did they do, especially when they had the stagecoaches and then later the trains? If they see those herds, they just stop them. People would lean out the windows and just kill as many as they could and then take off and go again. Senseless, totally senseless, how we destroyed portions of our ecosystem. So, yeah, I understand what you're saying there. But what I'm saying is the foods that we grow, this is going to be an issue. Because, okay, not too many, well, somewhere around the 1930s or 40s or so, we were really tough, and a tough thing about growing enough food for the Industrial Revolution. People were moving to the cities, populations were growing, there was more wealth around, and it was getting really tough to feed everybody. And there was a German chemist named Haber who developed a process where he could trap nitrogen from the air, and the air around us is 80%, 78 to 80% nitrogen. And nitrogen is essential for proteins. So growing crops, you have to have nitrogen. But the plants can't use the nitrogen in the air. But he developed a process that he took methane, okay, which is CH4, and with a lot of heat and different things like this, and the nitrogen gas made it into ammonia. And ammonia is NH3, or ammonium hydroxide is NH4OH, and that was a very rich source of nitrogen. He came up with that process of doing that, called the Haber process. It's spelled Haber, Haber, and that's responsible for what we later have called the Green Revolution. Suddenly we went from being really tight on growing enough, but now we can really grow, overproduce, really, because we have all this nitrogen fertilizer we didn't have before. Before that, nitrogen fertilizer came from bat droppings, okay? It was called guano or something like that, and it was sodium nitrate. And they go to the mines where it used to be caves where lots of bats pooped for many centuries, and they dig out all that stuff and sell it in bags. And that was a nitrogen fertilizer. We were using that up like crazy until he developed that process. Now, you would think that the chemist who developed this thing that allowed people to feed the world should have been really a well-recognized and celebrated chemist. And yet you don't really hear much about Franz Haber. Does anyone know why? Okay, I'm going to go back to a few things I said before. German, the 1930s or 40s? Yes. He was also the chemist who developed, yes, the gases to kill people in the chambers. He used those internees, you might say, the people in the concentration camp, as subjects for chemical experiments to find out what was the most effective at killing people and stuff like that. What's that?
He the reason why the little boy in striped pajamas died.
What's that?
Say yes.
The little boy in striped pajamas.
Yeah.
With his friends.
Yeah, right, yeah. So that's why he's not a very celebrated chemist. Even though he did some very good things, he did some really sick things too. So no one names their kids Robert. No. All right. Then the hydroxides are the OHs. We mentioned acids. Those all start with H. H2CO2, carbonic acid, H2SO4, that's sulfuric acid, HS, hydrosulfuric acid, hydrochloric acid, HCl. All those are the acids. Your hydroxides are the things that neutralize acids. Sodium hydroxide, potassium hydroxide, calcium hydroxide. That's in limestone, by the way. Well, it's calcium carbonate. But, you have these things that neutralize. Well, what happens when you take the H from an acid and the OH from a base? HOH. H2O. It makes water. Neutral. It neutralizes. So the hydroxides are other things, but you have things like most of your aluminum hydroxide, those are the aluminum ores that you get your aluminum from. Bauxite and other things like this. And then finally, number 8 is sort of a collection of things, your native elements. That would be your iron ore, your gold, your copper, your silver, those kinds of native elements that you just go and mine by itself. Very rare, that's what makes them very valuable, but those would be your native elements. And probably diamond would be included in that. That's all carbon. So those are your native elements. Sorry, that slide probably wasn't supposed to have lasted that long, but it did. Sorry. Okay, so let's look at how the silicates and non-silicates are divided. Now, it doesn't quite seem fair. The silicates here, 92% of the Earth's crust. These over here, 8%. Okay, so not nearly as much of this is here. But your minerals, and these are all your minerals, that's what we're doing, are classified as either silicates or non-silicates. In the crust, mostly silicates. Down when you get deeper, you get more of a mixture and less of these. But your silicates, your ferromagnesium silicates. Guess what 2 elements are in these? Ferro, iron, and some magnesium. Okay? Ferromagnesium silicates. For some reason, iron and magnesium, especially deep in the earth, they kind of go together. Okay? And then you have the non-ferromagnesium silicates, which basically have little to no iron in them. So basically the difference here, silicates, non-silicates, they have silica or they don't. And here, ferromagnesium silicates and non-ferromagnesium silicates, these have iron, these do not. So it's the almost dichotomous system, either yes or no. Some of your ferromagnesium silicates, and we'll see these again, that's the only reason I mention them. Biotite, hornblende, augite, and olivine. And these are kind of, not quite in the order that you'll find them, more toward the surface, but not that frequently. These are deeper as you go further down. Okay? The non-ferromagnesium silicates, these are mostly near the surface. These are lighter weight. Here's 2 things. If you have iron in there, they're denser because the iron weighs more. Okay. Also, if you have iron in there, they're usually darker. So when you say light, they're lightweight and light. Those would be the non-ferrous magnesium silicates. Light colored because they don't have iron. Lightweight because they don't have iron. Light in both in terms of weight or density and color. Quartz. We saw a picture of quartz not long ago. There, almost pure white or light colored anyway. Okay, so quartz, muscovite. What do they call it? White mica. Okay, very light colored, no iron in it. The feldspars. Okay, the feldspars can be a little bit darker, but the feldspars are your aluminum silicates, no iron, but aluminum silicates. And then there are subclasses of this. Plagioclase is also a feldspar. It's a sodium feldspar, so this is aluminum. This will be sodium aluminum silicate. Calcium feldspars, which are calcium aluminum silicates. And then you have orthoclase, which is potassium aluminum silicates. Okay? So you don't need to memorize all these, but just when you see the words sort of go in your mind, oh, non-ferromagnesium silicates, okay, the feldspars. And then you have the clay minerals. And we already mentioned kaolinite, or kaolin, illite. Now, what illite is basically weathered mica, okay? It has usually a lot of potassium in there. Potassium is that third group, nitrogen, phosphorus, potassium that we make in nutrients. So illite and muscovite, white mica, typically have good quantities of potassium in it. And then the chlorites, that's one of those 2-to-1 clays. I mentioned some of the others, but the chlorite, in fact, sometimes chlorites are called 2-to-2 clays. They're more complicated. But basically, your clay minerals are when other minerals have broken down, weathered away, and then they reform to make very small, tiny, small particle sizes. Those are your clay minerals. They still have crystal structure, but they're just really tiny. Okay, your non-silicates. Carbonate's the most common. Calcite, calcium carbonate. Dolomite, a mixture of calcium and magnesium carbonate. Sulfates, gypsum, calcium, sulfate, anhydrite, I think is aluminum sulfate, I don't remember. But they didn't put Epsom salts, which is magnesium sulfate. Your oxides, hematite is iron oxide. Magnetite is iron oxide. What's the difference in hematite and magnetite? That's it. They're exactly the same chemically, but one is magnetic and the other is not. So magnetite is magnetic. Hematite is not magnetic.
I know they sell hematite that is magnetic, but they say that that's not truly hematite because hematite does not have magnetic properties.
Right, exactly. That's what makes the hematite. Iron. Yeah.
But it looks different.
Yeah. Oh, it looks different too?
If I'm not mistaken.
I didn't know that. It may do. I mean, you may have two pieces of hematite that look somewhat different from each other because what stage of rusting they are or something like that. Limonite, I can't remember what oxide that is. And then you have all your aluminum oxides, which are also in your bauxite and other ores of aluminum. Your sulfides, remember this is just iron with oxygen, other things, aluminum with oxygen or whatever. Over here, your sulfides, pyrite is iron sulfide. Sphalerite, I don't remember what that one is. Galena, you'll see that again, I think, on the lab. And chalcopyrite, I think, is copper iron sulfide. So a bunch of those. Most of those come up from deep earth mining. Okay. The phosphate's the only kind we really have is apatite. It's a hard mineral, and again, sulfuric acid, that's what they use to dissolve the apatite, so you can get the phosphate fertilizer out of it. Okay? And then the halides are things like halite, that's sodium chloride. Fluoride would be probably sodium fluoride. Okay? And then your native elements, gold, silver, copper, diamond, sulfur, whatever else you're there. I assume platinum and other things like that you may. Yes?
When the leaves begin to change color,
Yeah.
is some type of chemical on them that makes them react to.
Okay. Yeah. Very good question. And I'm not absolutely certain I have the right answer to it. You can check with some of the biology people on this. But I believe what's happening is the plant knows it's going to go into the dormant season, so it really values that magnesium, so it pulls that out and the other parts of chlorophyll, and then you're left with just the basic structure, and that can be some of these other minerals that aren't as soluble, and they stay in there. And some of the reds could be iron. Some of the yellows could be reduced iron, but there's something else, maybe your sulfur. So it's just a residual. Because actually when the leaves turn the colors, you'll notice they're not as fleshy and stuff either. The plant is actually drawn out to store in the roots for next year, some of those minerals that they need to make it green again. So it's the residual stuff that doesn't dissolve. So it's stuff that's already in there, but in smaller quantities. You don't notice it until the green kind of fades away. Yes?
I actually kind of reminds me about a plant that's around here.
Right.
It's like if you touch it, it folds itself in.
Right.
It's not the
eaters.
It's not the fly eater.
Fly, you're right.
It's not one of those, but it's like that, I guess.
Yeah.
It has some of the same mechanics. If you touch it, it starts folding its leaves.
Yeah. Now, I can't remember what the reason for that is, but I have heard about it. It's some sort of protection mechanism, I think, but I don't know that for sure.
Little leaves and come along and they
Right.
span really big.
Right. And then they...
I think they're like elephant ears.
Oh, it could be, yeah. I know elephant ears will curl up, but that's when they're coming out. So I've heard what you're talking about, but I'm not all that familiar with it. Again, full of botanists. They'll know that a lot better than I. All right. Okay, here's some picture examples, and let's see if these are in your text as well. Yeah, both of these are in. If you see dark color, rocks, minerals, the high iron content. Compare the dark color of the ferromagnesium silicates, the iron content, augite here, hornblende here, and biotite in the middle, with the lighter colored non-ferromagnesium silicates you have here. Here's your quartz. See that distinct crystal? I think that's a hexagonal structure, okay? And let's see, non-ferromagnesium. Mica, that's the front and center. Now, something about mica, it comes in sheets. If you can edge those up, you can actually pull them off almost in sheets. They call it foliation. In fact, in the Midwest, when people were moving out there, of course, glass was really expensive, and I don't know if they had any places to do it, but they did have mica there, and they would take that and make their window. They weren't transparent, they were more translucent. They would let some light in, you just couldn't see in or out very easily, but they would use the mica for that. So that's right center here. The white and pink orthoclase, I think these are those up there, top and center, and quartz, which is over here, to the dark colored ferromagnesium here. Non-ferromagnesium silicates, ferromagnesium silicates. If you see dark colors, think iron content, high iron content. No dark color, think non-ferromagnesium silicates.
There's a place in Georgia I went to called the Hog Mines,
Uh-huh.
and I dug for crystals there.
Uh-huh.
And they have, I've got some tourmaline in here right now that I dug there. It's solid black, but it's got iron in it. I got some of the, what do you call it, the one that comes off the sheets?
Mica?
I got mica there,
Uh-huh.
and rose quartz. Regular
Oh, yeah, right.
and rose quartz.
Right.
All of this.
Yeah. The rose quartz are really pretty, but they actually have impurities in them to give them the red color. So I'll take it because it's so pretty. Yeah. All right. So the next subtopic here is physical properties of minerals. And basically, this is going to be your next lab. And I'm pretty sure we're not going to have time for it today because it's already almost 3. We have to start the lab at, actually, we should have started at 3:15 if we were going to do the lab. I don't think we're going to finish in time for that, so we'll just keep going, I guess. Some of the physical properties are color, and we're just talking about color. Color is not the best classifier because rose quartz and regular quartz, really the color is very strikingly different, and yet it's all quartz. I mean, it basically is the same stuff. It's just the rose quartz has very slight amounts of impurities in them, but they're just enough to change the color. They can be influenced by trace impurities. That's what I just said. I didn't realize that was on the slide. Now, surprisingly, a better classifier would be the streak. What you do is take the mineral you have, and if you have a really rough surface that will actually scratch the thing, rub it across there, and that leaves a streak. That color is a good classifier. The color of the mineral, when finely powdered, very much more consistent than the color itself, the color of the mineral. The finely powdered, that gives you. Of course, if you have a very, very valuable mineral, you don't want to grind it into a powder, but that would be. Another is hardness, okay? And a lot of your crystals and things like this you compare by the hardnesses, but this is the resistance to scratching. That's why I said if you have a material that will scratch it, some won't, okay? And what they came up with, some guy named Mose, and this wasn't Larry and Curly's friend, no, okay? This was, he came up with this hardness scale. Uses 10 test minerals of increasing hardness, and that's what the scale is. Let's see if we have it here. I think we do. Yeah, here we have. The softest of your minerals is talc, and that's 1 on the Mohs hardness scale. What do we use talc for? Powder. Yeah, oh boy, that makes your skin feel so soft. Okay. Next is gypsum, not very hard at all. In fact, that gypsum board, you can take your fingernail and scratch that gypsum. It's pretty soft. Not as soft as talc, but number 2 on the most hardness scale. Calcite is next. Now, calcite is the mineral that makes up limestone that's calcium carbonate. And we'll see in the next lab, I'll take you around and show you some of the actual samples of that calcite. It's hard feeling, but you can still scratch it. Okay? Fluorite. Now, that's not a super common mineral, but it is one that's number 4 on the hardness scale. Apatite, you know what that was? How hungry you? No. What was it? What was your appetite? It's the phosphate mineral, where you find the phosphate. Mostly calcium phosphate, but it has lots of other stuff in it too. That's pretty hard, but about midway to the scale. Orthoclase. Now, if you remember orthoclase, that showed up here. Orthoclase was potassium, aluminum, silicate. Okay, that's number 6 on the hardness scale. Quartz, that was silicon dioxide, basically, and that's number 7. Now, what's another sort of common name for quartz? Second?
Crystal?
Okay, yeah, all these are crystals, okay? But what? Quartz. Most of your beach sand is quartz, okay? And what do we use sand for? And yeah, you make glass out of it, but you don't let it crystallize. You cool it real quickly. But what do? We make sandpaper, which you can soften any of these things because the quartz is harder than all these. So woods or anything else you can polish with sandpaper. Okay? But you can't do these things here with sandpaper. Okay? If it's really sand. Topaz is one of those, what is the name they give those? Semi-precious, or they have a name for it. And what color is that? Is that the blue or is that the red? Topaz. Second?
Is it brown?
Topaz? I don't know. I always forget.
It was like a cyan.
What's that?
I thought it was like a cyan or
Is it?
blue.
Okay, yeah, bluish. That's what I was thinking. The topaz. Pretty hard, number 8. But if something won't work with sandpaper, another better thing is corundum. And sometimes you'll find that. That's number 9. But nothing's going to touch diamond. If you want something that's going to cut through anything, get a diamond thing, like diamond impregnated metal or something like that. Those blades will cut anything, okay? Concrete, steel, whatever. That's the hardest, number 10 on the scale. Now, some of the common objects are sometimes used for comparison rather than the actual test mineral. Here are some of the common objects. The fingernail is 2.5. It'll scratch gypsum but won't scratch calcite. Okay? A copper penny. Do I have one? The trouble is, most pennies aren't copper anymore. Okay? Because that much copper is more than a penny's worth, so they put some cheap metal in it too. So, but anyway, if you can scratch it with that, that's 3.5. Harder than calcite, but not as hard as fluoride. Okay? Ordinary glass, it ranges as 5 to 6, so between apatite and orthoclase. And a pocket knife blade is also 5 to 6. You're not going to be able to scratch quartz with a pocket knife blade, but you will scratch these blades down here. Be careful with pocket knife blades, though. Okay? They will cut through skin pretty easily. Okay. Now, more. That just gave you 3, color, streak, and hardness. More physical properties are the crystal form. Okay? Now, we have the 6 basic groups we already talked about. You don't have to know those or memorize them. But what you do need to know is recognize when you see them in tables and stuff, related to the internal geometric arrangement of atoms. Now, I took a whole course, and it was still confusing in how you name and deal with crystal. It's a crystallography course. Basically, when you do your lab, you're going to do it on the computer, and when you see things like 101 or 0110 or something like that, that's referring to the internal geometric arrangements of the crystals. So when it says, you'll see that, okay? And that also relates to the cleavage. Cleavage is the tendency of minerals to break along smooth planes. We saw that in the micas. I mean, talk about breaking in smooth planes. I mean, that does. Between the sheets is very easy to break. Harder to break this way, but easy to break that way. The quartz, they'll break this way and this way, but to break that, you need something really, really hard. And even diamond. That's what the master jewelers do. There is a name for it. What do you call the people that do it? Diamond cutters is what I call them. But if they can find that cleavage plane and hit it, even though diamond's the hardest material there, they can hit it right on the right place. They can shape the diamond in exactly the form that's going to give you the most brilliance and the most refraction. And that's truly an art as well as a science. So that's the cleavage, the tendency of a mineral to break along the smooth planes. It's related to the crystal form. Now, on the lab you're going to do, it'll say cleavage/fracture. Some things won't cleave, they'll just fracture. And that's what happens if you hit those things wrong. Big, beautiful diamond, hit it wrong, you just lost millions of dollars worth of value there. Okay, but that's the irregularity in broken surfaces. That's when it's fractures rather than cleaves. Okay, so on your lab, you'll have cleavage/fracture, and usually they put that in the table, and you just write down what you see. All right, luster. Okay, that's the surface sheen of the mineral. Okay, and there's several different ones. A metallic sheen is going to sort of look like a metal. Pearly is like a pearl, but it's sort of a milky kind of a sheen to it. Vitreous is a sort of a watery type look to it, and there's several others, and you'll see those in the table too when you do it in the lab. And then this one is probably the best classifier, and that's density. Density is a mass to volume ratio. Just knowing the mass of a substance doesn't give you a clue of what the substance is. Knowing the volume of a substance, not a clue. But if you have the mass to volume ratio, that almost uniquely identifies the material. Okay? That's what density is, mass to volume ratio. So the units for that are usually in grams per cubic centimeter. Density has units. Mass is measured in grams, volume in cubic centimeters. Okay. But sometimes they'll call it density, but it really isn't. The alternative would be specific gravity. That's the ratio of the mineral density to the ratio to the density of water. But in grams per cubic centimeter, guess what the density of water is? 1 gram per cubic centimeter. So if you divide by 1 gram per cubic centimeter, you lose the units, and specific gravity is a pure number. So if it's given with units, that's the density. If it's given without units, that's specific gravity. Okay? So when you're doing your lab, you'll see that you can either give it as density or specific gravity. Okay? And then 2 factors contribute to density. Number 1, the kind of atoms making up the mineral. I've already mentioned that. What makes most of your denser minerals dense? How much iron content they have. Because iron is a dense element. Okay? So the kinds of, if it's made up mostly of silicon and oxygen, those are lightweights. Okay? So they'll have low density. If it's made up mostly of iron and copper or some of those things, those would be much more dense. Certainly if it has any gold or things like that. That's one thing. The kind of atoms making up the mineral. What are those? If they're dense atoms, they tend to be a denser mineral. But another thing is the way that the atoms are packed into the crystal lattice. If you have a very open lattice structure, that will have low density. Whereas really packing them in there on certain of the crystal structures, you can have a lighter weight materials that also is denser because you got more packed into a smaller volume. Now, here is an example, and this isn't really a mineral, but it has a crystal structure. What is the most common compound on the surface of the earth? More common. On the surface of the earth. Water. Most of the earth is covered with water, right? Okay. Now, water is a liquid form at normal temperatures and pressure, right? If you heat it up, it can become a gas. If you cool it, it can become a solid. Okay? All at fairly normal temperatures and pressures, right? Most things, when you heat them, they expand, so they become less dense. When you cool them, they contract and they become more dense. Can you think of an exception to that? We just mentioned water. Do you happen to have anything in your McDonald's stuff there?
No.
Oh, okay, you don't?
Yeah.
Is it?
You need a cup?
No, I'm just wondering. Do you have anything in there?
Ice.
Ice. Now, if you put water in that, what would happen?
The ice would melt.
Okay, it would. But what would it do before it melted? Would it sit at the bottom?
Yes.
Well, wait a minute. Ice is solid water. You would think if it became solid, it would become more dense, right? But because it floats, it must be less dense. The reason for that, and frankly, there are very few, if any, other liquids that when they solidify, they become less dense. Water is almost unique in that way. And if it weren't, we probably would not have life on this planet as we know it. Because if ice, water, when it froze, sunk to the bottom, then all your Arctic oceans, or all your lakes and streams in northern environments, when they would freeze, they'd freeze from the bottom up. And you kill every bit of life in it. You wouldn't have fish, and you break that cycle, and we probably wouldn't exist, because we're part of that cycle, folks. But because ice expands when it freezes, then ice floats, and then you always have liquid water underneath ice, even at the North Pole. You have an ice cap and liquid water underneath, so you still have animals living there, and plants, and all sorts of life in there. If it froze the other way, like most things do, death to those animals and some of those plants. We wouldn't have the ecosystem we do today if water didn't. Okay, really bizarre. Well, what happens? Water, remember, has that hydrogen bonding that really ties those molecules close together. Then when it starts freezing, they have to get in the crystal structure. It forces them further apart, and that's what makes it less dense. So the packing of the atoms in the crystal lattice, water packs less tightly as a solid than it does as a liquid. Now, that's not a mineral, but yeah, that's just an example of how you pack things. That makes a difference. Okay. More physical properties. These are just illustrations of this. This is a piece of mica, I'm pretty sure. This is gypsum with a hardness of 2. Your fingernail is 2.5. Notice how just scratching your fingernail, you can scratch the gypsum. Now, that's not what gypsum board looks like. That's almost translucent, but there you have it. Whereas here, quartz, hardness of 7, scratch away, folks. You're never going to mar the surface of that. And again, you see that hexagonal structure there. Beautiful, beautiful crystal. Okay? Even if you had a metal file, you can file away all you want. You're just going to make your metal file go dull. Okay? You will not scratch that quartz. Okay? Because metal files are like knife blades, around 5 to 6, maybe 7 if it's a really hard metal. Quartz is what? 8? I don't remember. 7 or 8. Okay. Now, those were the physical properties of minerals. And by the way, on the bottom of page 442, when it says grow your own, they're talking about minerals, folks. Never mind. Okay. 17.3 are the mineral forming processes. Okay? Mineral forming processes. Formation of minerals happens in 2 liquid environments. You may not think of one as a liquid environment, but it is. But the first of these, when you think liquid, you usually think water, right? Okay. So, crystals form from highly concentrated ions. Now, what would that concentrate ions, you think? Losing some of the water. Okay? Think of this. Have you ever gone cook you some beans, right? So you put the pot of water on the stove, probably add some salt to it, and you're going to let it come to a boil, and then you're going to drop your beans in there, right? But you got busy and carried away with something, got on the telephone or something, and forgot about it, and what happens? The water evaporates, leaving salt crystals all over the bottom of the pan. The salt crystals, when you put it in there, they all dissolve, right? But as you lose the water, you concentrate the salt crystals, then they go back into crystals. And this is how you grow your own crystals. Whatever you're trying to grow, you concentrate the ions in there and then let the water or the liquid, whatever it's going to be, you lose it slowly. If you lose it rapidly, you get little crystals. Lose it slowly, you get big crystals. Okay? So water solutions, crystals form from highly concentrated ions. Now, the other thing that does, let's go back, maybe not salt in water, but let's do sugar in water. That's another crystal, right? Okay? How do you dissolve sugar in water most effectively? Second? Warm water, exactly, because warm water will dissolve crystals much easier than cold water will. Why is that? Because there's more energy there, the molecules are bumping around, they're further apart, so it's easier for the ions to be dissolved. But as you chill that water, think of iced tea. That's unsweet tea and you put sugar in it. But it's iced tea. You can stir and stir and stir until you finally melt all the ice and stir enough to get it boiled. You're going to have sugar crystals at the bottom. Put that same amount of sugar in hot tea, disappears before it even reaches the bottom. So think about this. Where where does most of the water wind up? Okay, yeah. But liquid water, where does it wind up? Okay, a lot goes into the ground, but a lot stays on the surface, and where does it wind up? Back in the ocean, exactly. And as that water is going, falling on the soil and dissolving things as it goes, as soon as that water hits, it starts dissolving stuff or picking up stuff. And it all dissolves and stuff and goes down the river. You don't drink river water. You don't drink creek water usually either. The further down it gets, the less likely you are to drink it because it's got all sorts of stuff in it. Finally gets to the Gulf of Mexico or the ocean or something like that and evaporates. Well, guess what? You're building up concentration of those ions that you dissolved up here. You're losing the water but keeping the ions. Now, you go real deep, really deep into even the Gulf of Mexico. This surprised me. I always think the Gulf of Mexico is a warm bathtub, because water is always warm and stuff like this. I did not realize until the Gulf oil spill, when you go down a mile in, I didn't know the Gulf was that deep. A mile deep, that's where the rupture occurred. It is almost 0 degrees down there. I mean, it is cold. On the surface, 70, 80 degrees. Down there, almost 0 degrees. And guess what? Things come out of solution there. The ions are concentrated because water is evaporated away, but also the temperature goes down, they come out in solution. So crystals form from highly concentrated ions, either from evaporation or cooling or both. Now the other liquid environment is from very hot stuff, magma. What is magma? Molten rock. What does molten mean? Actually, melted. Same root word. Liquid rock from which minerals can crystallize. Okay? Now, they do this at the steel mills all the time, don't they? Yep. Whatever you got there, you're heating that and heating it until it melts. And then what you do, some things melt faster. Sometimes when they're re-cooling, things will come out and you pull off the slag. Yes, exactly. And that kind of stuff, the impurities. And then the steel itself stays molten until the very end. And you get rid of all the impurities. That's why they heat it up that way. So the molten rock, the liquid rock, from which minerals can crystallize. That slag crystallizes before the steel does, right? And that's why you can yank it off of there. Well, this happens naturally in nature. When you have molten rock way below magma, and when it comes toward the surface and starts cooling, certain things come out first, and then others later, and others later. Okay? Yes.
That's the way they do gold. When they gut gold, they put something in there and get all the impurities out.
Right.
And it goes to the side of the pot.
Right. Okay. I didn't know how that happened.
Yeah. They do that. And also crystal. You were talking about crystal. It's some type of crystal that you can put in soil, and it soils the water.
Oh,
and then once you heard of that?
Okay, go on.
And then once the soil gets dry, it releases the water.
Yes, right, exactly. They call it water shakers or something like that. Those crystals, we bought a few bags of potting soil, and it says it comes with that in it. And
but you can also buy it.
You can buy it, put it in.
Yeah.
Perlite, I think, is one of them. And goodness, I know the other name, and I can't think of it right now. But those are things that, like you say, the crystals absorb water as you wet things and keep from overwatering plants. Then as the soil dries, it releases the water. And actually, we'll talk about, in another chapter or two, we'll talk about humus. Not hummus. Hummus is what you eat on Mediterranean food, but humus actually does sort of the same type thing. If you can get that mixed in your good organic matter, that does the same type thing for you. Okay? So you're absolutely right. So the magma can crystallize. That can happen below or above the Earth's surface. If it happens below the Earth's surface, usually that happens more slowly. And if it happens more slowly, the crystals are usually larger. If it happens on or above the Earth's surface, they cool really quickly, so your crystals are very small. If they've even formed crystals at all. Yes?
It's 320. When were you supposed to cut the screencast off?
The what?
When were you supposed to cut the screencast off?
Oh.
Remind me.
Okay, when I was supposed to turn it off? Is that what you're asking?
Yes,
Around. You mean to take roll again?
Yes.
Okay, yeah. I do that at 3:45. And it's what now, 3:20? Okay, around 3:45. If you remind me again at 3:45, I'll stop and call roll again. I have to account for class and lab time, even though whether we do lab or not, the system requires us to put it in twice. Okay? So, if it happens, if the molten rock recrystallizes below the Earth's surface, usually the crystals are larger, and usually the things that come out of solution first come out there. Okay. On or above the Earth's surface is usually smaller. Now, magma is molten rock below the Earth's surface. Once it reaches the Earth's surface, we don't longer call it magma, we now call it lava. Magma forced out of the Earth's surface into the air, basically, or into the water. Okay, sometimes this is underwater as well. That's when it becomes lava. Okay? Now, that forms crystals, minerals. Okay? What are the factors that contribute to those forming processes? Well, we've already hit one here, and actually one here too. Temperature. Okay? The hotter something is, different minerals come out at different temperatures, like you said, the slag, okay, and other things like that. And temperature also modifies and changes things. We'll talk about that later in this chapter. Pressure, okay. Two forms of carbon, okay. I think we mentioned them both today already. What is that black carbon that's in a pencil there? Graphite. Graphite is two-dimensional crystal of carbon. Okay? Basically, the soot in your chimney is almost graphite. It's slick, right? Actually, they use graphite sometimes as a lubricant. Two-dimensional crystals, really slick. Okay? That's the kind of lubricant I don't want to get on my hands because it's almost impossible to wash off. Okay? Now, another form of carbon, three-dimensional crystal carbon, is what? We mentioned it already today. On Mohs hardness scale. Number 10. Diamond. Carbon. Pure carbon. Black, sooty, slick stuff, two-dimensional crystal graphite, three-dimensional crystal carbon, diamond. Clear, brilliant, refracting. Same element, same atoms, different crystal structure. Boy, the crystal structure can make a lot of difference. What made the difference there? Pressure. Diamonds are made under enormous pressure and time. Whereas two-dimensional graphite happens very quickly, okay? Low pressure, short periods of time. And probably temperature has to do with it as well. The other thing, important factor, is the availability and concentration of the ions in the solution. Thinking water solutions then, but it also could be the molten solution of rock too. What is in there, that's going to determine what kind of minerals come out. Now, when you say glass, you think of that clear stuff, right? But what a glass is a rapidly cooled solid that lacks a crystal structure. It cools so rapidly, it doesn't have time to form into the crystal structure. Okay? That's how you make glass. You take sand particles, quartz, heat it up, break it down, melt it, but then cool it so quickly it doesn't have a chance to get back in that crystal structure. That's what makes glass glass. But,
sea glass.
second,
That's sea glass.
okay, and what do you mean by sea glass?
Isn't that a thing? Like,
I think so, but what do you mean by it? That's what I was
like, because obviously it's not something that's been melted down. Doesn't it happen in nature? Sea
Yeah.
glass?
okay. Oh, well, that's what I was trying to get you to say. There is a thing called volcanic glass.
Okay, yeah.
Okay, and that's when the lava, when the magma comes to the surface, becomes lava on the surface and cools really quickly. Sometimes those rocks are shiny, clear. In fact, they have a name for them: obsidian. Any of you Game of Thrones fans? Okay, a couple people jerked out. Obsidian is what they made the swords that will kill the whites or something like that. Is that right? I don't know. That's science fiction or just fiction. Okay, maybe no science involved.
Peruvian steel or something. If that's what you're the daggers or swords anyway.
I don't know. I read the books a long time ago, and I got tired of that for a while. But I've never seen the show. But anyway, they talked about the obsidian, which is volcanic glass. Okay. It lacks a crystal structure, but it has that.
Oh, the dragon glass.
Yeah, that may be it.
The dragon glass, yes.
Yeah.
Particular glass
Yeah.
that they
So
mine.
I'm guessing when you said sea glass, it's probably maybe volcanic material that cooled really quickly in the sea. I don't know. That's why I was asking you what it was exactly. So that could be sea glass. I'm guessing. Okay. I do a lot of guessing. My wife says, wait, he can make anything sound reasonable, so, whether it's true or not. So when you ask me some of these questions, I'll give you my best guess, but that's all it is. A wild guess. Okay. A wag. Okay. Now, let's look at some minerals formed at very high temperatures. This is the Bowen's reaction series. This sort of illustrates all of this. These are mostly your silicates. What two kinds of silicates do we have? Okay. Now those are, okay. There's two kinds of stuff on the surface of the planet, silicates or non-silicate. Silicates are 92% of the crust, 8% are the non-silicates. That's it. But among the silicates, what two classifications do we have?
Chain and sheet.
Second?
Chain silicate.
Iron silicate, is that what you said?
Chain, no.
No. It's the ferromagnesium silicates and the non-ferromagnesium silicates. The silicates that have high amounts of iron and those that don't. So this is the silicate crystallization sequence for those silicates, Bowen's reaction series. The ferromagnetic silicates, they crystallize at the highest temperatures. That's why they're usually deepest in the ocean, in the earth, because they crystallize before they ever make it to the surface. Now, when magma erupts, yeah, some of that comes up. It doesn't have time to crystallize underneath, but that's ferromagnesium. The minerals crystallizing later are progressively richer in silicon and poorer in iron. They still are silicates, but they're richer and richer in silicon, like quartz. Okay, so here's Bowen's magnesium reaction series. Okay, now on this side you have your irons. Now these are usually hotter than these, so they put them as if they're almost the same. Your olivines come out first. That's why they're the deepest. Okay, because they come out of the magma at very high temperatures. They crystallize out early. Then augite, and I told you this before when they listed these, augite, then your hornblende, and then your biotite. Most of what we'll see on the surface will typically be more biotite than olivine. Olivine will be much deeper. Not always, but most of the time. Okay. On the other side, your non-ferromagnesium silicates, those are your plagioclase feldspars, and remember those are calcium to sodium, going in that order. Then your potassium feldspars, then your muscovite, white mica, and then your quartz. Quartz is the last to come out at the coolest temperature before those crystals form. And that's why a lot of your sand grains and things like that right on the surface, they come out. But those big chunks of quartz, they had to do it very slowly, but it'll still be at very much cooler temperatures. Okay? And again, you don't need to know this, but know what it's telling you. Okay? You want a break?
Yeah, I thought you said break.
Okay, I don't know what you said, but it sounds like a good idea to
I
me.
said break.
Okay, and maybe that's when you said pause the screencast-o-matic. Let's see. We'll begin next time. So these are minerals formed at high temperatures. Then we'll come back and do those formed at normal temperatures. So we'll start with that. All right, well, I got about 5 minutes or so before I need to call roll again. So I'll give a chance for other stragglers to make it back in. Now let's talk, well, let's see, let's get the thing back up. Any questions on what we've done so far? I'm sorry, I'm taking way too long on this chapter, but y'all seem engaged. I'll do it. Maybe it's just me. Okay. We looked at minerals formed at high temperatures. What series did we use for that? What series did we use for that? Bowen, reaction series, exactly. Now we're going to consider minerals formed at normal temperatures. Okay? These are formed at the Earth's surface in contact with oxygen, carbon dioxide, and water. Okay? Guess what? Oxygen and carbon dioxide, what are they going to form? Carbonates. Okay, good guess. Okay. If you have sulfur around, like you have in the environment, sulfur gases in the atmosphere, you can form sulfates. Certainly if you have oxygen, especially with water. Water tends to be a catalyst to form your oxides. So that's where you form your oxides. Your halides, well, those are those commonly occurring lightweight category 7 elements there, formed with other things. So those are your halides, and then your sulfides. Now, a lot of sulfides will also form deep, and then they come to the surface later, but those are usually formed in more normal temperatures and pressures. Now, except for the oxides, the others that we mentioned here, the carbonates, the sulfates, the halides, and the sulfides, are lower hardnesses and lower specific gravities than minerals formed at very high temperatures. Because quite often high temperatures come with high pressures, and when you have that, you tend to have large or very hard materials and pretty dense materials. Okay? Not always, but quite often you do. So these will form the things, the lighter weight minerals that form near the surface. Okay? Quite a bit on that slide. Okay. Yeah, these are, yeah. Now, these are all out there already, okay? I got everything out there on Blackboard except the grades. That's the only thing that's out. The PowerPoints are there in static form, and then they'll also be there through the YouTube videos. You'll see these two. So you can go back and pick up anything you may have missed. Oh, and by the way, right at break time, a couple people came up either to get the lab they missed last time, and one person actually got a test they missed, I guess, time before last, or whenever we had the test. So if any of you need those, you know, at the end of, between now and test time or after you turn in the test, be sure you get those. And again, about the last lab, 3 questions on the lab. First 3 questions on the lab depend on what you observe of the moon, hopefully between now and the end of the term. Now, the moon's only going to be visible for about another week, and then it won't be visible for a while. Well, it depends on what time of day you're looking at. Morning will be different from evening, but, you know, depending on what time you're looking, maybe only about a week you'll see it, and then you won't see it for a couple weeks, and then you'll see it again. Or if you're doing the early morning hours, you probably, didn't someone say you saw the moon come up right around 8 or so? Yeah. So therefore, it's probably set by, did you say you look for it in the morning? Yeah, okay, yeah. It's up for about 8 hours. I mean, 12 hours. So if it came up about 8, it wouldn't set till around 8. So if you were earlier than that, you saw the moon. But it was probably getting ready to set. Yeah, yeah, it would have been up visible then, yeah. But then later, right, yeah, that's because it was beginning to get too light. So that's why you either need to get up earlier or stay up a little later at night to view it. So you can hopefully see some stars. Okay? So if anyone just got the lab today, those first 3 questions, I go into gory detail of how you make those observations, when you make the observations, that kind of stuff. It's all on the lab, but I go into it more, so listen to it on YouTube. But then, the last bunches of questions from Part B on, those are, we did in class, you'll have to get those off of YouTube. And you can get them, I think they're all pretty obvious there.
Except I don't think we recorded the first portion of that lab.
Yeah, but the part that we did, the Part B, I think we got all that.
Oh,
It was just some of the observation stuff I missed.
Okay.
So you'll have to read the lab to get those. Okay, you're right. I forgot that. Okay. Oh, and also, by the way, everybody had turned in the first test, and I can't remember if everybody was here to get those back. If you weren't here last time, you probably didn't get it back. Let me see if I can find those. Okay. Hunter? You took your lab, I think. You got it early. Yeah. Okay. Trey? Anthony? Did you get a copy of the lab? Kira? There you go. All right. Well, recalcitrant, sorry. Now, I'm guessing since y'all didn't get those things back, you probably don't have copies of the last lab either, right? So get those before you leave today. Okay. All right. Done? All right. Yeah, it's time to take roll. Hunter's still here, mostly. LaShandra's still here. Rachel's still here. Trey's still here. Ray's still here. Jarrell's still here. And Cece's still here. Anthony's still here. Sean's still here. Fred didn't make it in today. You said he probably wouldn't, all right? Chelsea's still here. Sam's still here. Nick's still here. Melva's still here. Willie's still here. Lisa's still here. Tiara's still here. Anhil's still here. Ashlyn didn't make it in today. And Kedrick didn't make it in today. Bottom part of the alphabet fell apart there, but other than that, pretty good attendance. Good way to go, folks. And hopefully by next time I'll have you in the roll book, but I just can't sit down and get that done. All right. So, minerals formed at normal temperatures. Now we have another class here they called altered minerals. Okay? And this isn't in the book as much as it was in the earlier editions. So what do we mean by this? Sometimes exposure to different environmental pressures, remember we've seen these before, temperatures, and now sort of a new one, chemical solutions, can change minerals into new ones. Okay? We'll talk about this even more so in the second half of this chapter. I'm not sure it's half, but second part of this chapter, where we talk about rocks. But that also goes for the minerals that make those rocks. Now, generally, these changes occur above 150 degrees Celsius. That's pretty hot. What's 100 degrees Celsius? Boiling point of water. So this is another 50 degrees Celsius above that. So it's very hot, but look at that pressure. 2,000 atmospheres of pressure. Now, what do we have above us right now? 1 atmosphere of pressure, approximately. That's about 14.7 pounds per every square inch of our bodies. Okay? So that's a fair amount of pressure. Okay? Now, I don't know if any of you have done any scuba diving, but if you think about it, if you go down into a very deep pool and you go 10 meters down, that would be, this is about a 3-meter story here. So 10 meters would be like a 3-story building, plus a little. So the tallest part of this building here, that would be about 10 meters. Okay? Wait a minute, that's not right.
Have you been scuba diving?
What's that?
Have you done
No.
scuba diving?
Okay. But if you go 10 meters down, which is a little longer than 10 yards. All of you watch football. 10 yards on the football field. Do that, huh? No, a meter is a little bit longer. A yard is about like this. A meter is about like that. About 3 inches longer or something like that. Yeah. Okay? So, 10 yards. A little bit more than 10 yards. That's 10 meters. You go, that's 10 meters of water is 1 more atmosphere of pressure. Think about all the weight that 10 meters of water would be on you. That's another atmosphere of pressure. Go another 10 meters down. Now you're at 3 atmospheres of pressure. Think how deep you'd have to go to get 2,000 atmospheres of pressure. Well, you're not just below water, you're below rock. You're deep in there, way deep in there. Okay? That many atmospheres of pressure. Okay? Now, some of these, and they do a pretty poor job of this, but garnet probably was some other minerals before, but when you get that much pressure on it, it changes the garnet. Is that the green one? Okay. Okay.
You don't know which one garnet is?
What's that?
You don't know which one garnet is?
No.
It's your birthstone.
I know, it's one of the birthstones.
Yeah, it's yours.
It's mine.
Birthstone.
January?
I'm on 6, you're on 7.
Oh, really? Okay.
You know?
Yeah. Garnet is red?
Yeah, red.
Oh, red.
Yeah,
Okay.
remind you of rubies.
Okay.
Yeah, it's got it's a little more on the pink side. But
Okay. Epidote, I don't know for sure what that is, but it's a mineral. Talc, I would have thought talc would not be altered. I thought that would be a very mild one. But in the graphite, they said it's altered. Okay? Serpentine is one of the asbestos sources. That's why I said it's one of those chain silicates. And that is an altered mineral. Now, that's all they say about it. Don't sweat that too much, because obviously they don't say too much. It's not going to probably show up very much. But things do change with lots of temperature and lots of pressure. The actual chemical bonding changes. Okay? Now let's consider the ore minerals. Okay? That was that last classification, remember, of your non-silicate minerals. There's 8 classes. The number 8, the rarest, were your ore minerals. The mineral deposits with economic value, gold, copper, silver, often found in veins. What in the world are veins? Thin, flat bodies of the mineral material, which indicates to me that something was happening there. Either they deposited selectively, that made the thin, flat bodies, the veins, or chemically something was happening that drew them together into one general location. They say here that often is left over from crystallizing magma and flushed away in hot solutions. So maybe they hadn't quite solidified or solidified first, and then they were flushed away in hot water solutions or maybe mild chemical solutions and then reformed. Here are some examples. Pyrite, which is iron sulfide, as we said before, fool's gold, and chalcopyrite, which is the sulfide of copper and iron. It's copper iron sulfide. Sulfide, not sulfide, sulfide. Okay? Now, somehow to me, these examples don't quite fit the ore mineral category. Because if it's iron sulfide, that's not an ore of iron. You do have a fair amount of iron in it, but that's something else. I think that maybe belonged on the last slide. And chalcopyrite would be sulfide of copper and iron. I think your iron ore is basically olivine or biotite or something else. I mean, it's one of those things, or just almost pure iron. So I don't really care for that example. It doesn't seem to fit the rest of the slide. Okay? All right. Now, remember this chapter had a multiple title? Title was Rocks and Minerals. But guess what? We did the minerals first, and now we're going to do the rocks. So we're in the second part of the chapter now, which was the first in the name, but it's the second here. What in the world is a rock? Okay? Besides a country? No. Okay? A rock is an aggregation. That means a bunch of stuff has come together, and it could be of just one mineral, but most likely more than one mineral, and perhaps some other materials that aren't really mineral. Okay, we'll see some examples of this. Minerals are physically combined to make rocks. Okay, so let's say we have some biotite. That's ferromagnesium silicate. Happens usually sort of more close to the surface, but it's also bound together with some quartz. Well, biotite is dark colored, and quartz is light colored, and maybe some feldspars, which is sort of brownish colored. What I'm just describing is a piece of granite. It has more than one mineral in it. Aggregations of more than one mineral, one or more than one mineral, somehow physically combined with others to make rocks. So rocks are an aggregate of one or more than one kinds of minerals.
So when you see the little smooth pebbles, rocks, what make them that little form, that shape? You know, you can find those pebbles and
yeah.
It just be round.
Yeah. Now, what has happened there, whatever rock that was, the odds are that's been in the presence of flowing water for a long time. You call those sometimes river rock because water has eroded away the roughness of the surface and left that round pebble. So the shape of it mostly is what's happened after it formed. Okay, and that's what makes those. Quite often, the unusual shapes come from some sort of weathering, and we'll talk about that in 2 chapters. Okay, we'll get to that. So, how do we classify rocks? Okay, dumb as rock? No, that's not right. Okay, how do we classify? It's based on how the rocks were formed. 3 main groups of rocks: igneous rocks, sedimentary rocks, and metamorphic rocks. Now, does anyone know what igneous rocks mean? Where did that come from? Say again? Hey, very good. Formed by lava. If you change the ES here and put an ITE, what do you have? Ignite. So these came from hot environments. In other words, melted rock. They were lava. They were magma, and they became rock. Those are your igneous rock. They solidified from magma or lava. Okay? We'll go on to the other two later. Sedimentary, they came after settling. Okay? And then metamorphic, they metamorphosized. Can't think of the author who wrote the book, The Cockroach, or something like that, or the weird. But anyway, that's metamorphic. We'll get to that later. Okay? So let's look at igneous rock. Formed from magma, okay? I don't really like formed from magma above or below the Earth's surface. If magma was above the Earth's surface, it's actually lava, okay? So either formed from lava or magma below the Earth's surface. Here's a good statement. All rock were at one time igneous rock. That's the first rock you ever had, were igneous rock. Then the others formed from that, okay? Now, another good statement. We'll say this about 10 different ways. The cooling rate determines the texture of the rock. Okay? And we'll talk about this in a little bit. The slower the cooling rate, generally the larger the crystal. So the coarser the texture. On the other hand, the more rapid the cooling rate, the smaller the crystal size, and therefore the finer the texture. Okay? Cooling rate determines the texture. Okay? Here is a picture of sort of what I was describing before. You see the occasional little dark spots in there? That's probably biotite, the mineral biotite. I'm just guessing. The whitish crystals in there, the odds are that is quartz. Okay? And the brownish kind of crystals you see in there, that would probably be a plagioclase, a feldspar, something like that. That's a mixture of several. It's a type of igneous rock, okay? It's made from molten matter material. These are fairly good-sized grains. They don't look huge, but fairly large grains. This is a sample of granite. Now, that may not look exactly like your ideal countertop, but you see they've taken that and polished it very, very smoothly, but you'll see those colors in it. Okay? We'll get to that a little bit later. Now, two types of igneous rock. We love to classify, don't we? Three types of rock. What are they? Igneous, sedimentary, metamorphic. Two types of igneous. Intrusive, extrusive. Now, you can almost tell by the name there. Intrusive means interior. They cooled, they formed, they crystallized beneath the surface of the earth, inside the earth. Usually slow cooling. And if they cool slowly, what does that mean? Larger crystal size, coarser grain. Exactly. Okay? The extrusive igneous rock were those outside, formed from lava on the surface or above the surface. That would produce rapid cooling, and that would produce small crystals, very fine grains. Okay? If it cooled too quickly, here's a picture of obsidian. Okay? If it formed too quickly, what does that almost look like, except for the color of it? It's shining like glass, and that's volcanic glass. This piece of obsidian, which has the same chemical composition of this thing right here, granite. Chemically, they're identical. But they don't look identical, do they? Okay? So, the obsidian is a different texture because it has no grains at all. Okay? It did not form crystals. It's a volcanic glass. Another fracture. I can't read that. Something fractured surface. I don't think this figure. Oh, here it is. The curved fracture surface is common in non-crystalline substances such as glass. See, you don't get any grain to it at all. It's just a smooth curved surface. That's a glass. Cool too quickly for the crystals to form at all. Okay? Continuing with the igneous rock classification. 2 factors that contribute to that. Okay? So what kind of igneous rocks you have. One is what the mineral composition is. Okay? Is it higher in ferromagnesium silicates or higher in non-ferromagnesium silicates? Okay? That's one factor. The second, texture. Fine texture, coarse texture. Meaning large crystal size or small crystal size. Okay? So, mineral composition, non-ferrous composition is on the left of the figure. Let's show the figure. Okay? Non-ferromagnesium here. The further you are to the left, the less iron content. The further you are to the right, the larger the iron content. And there you see your olivines. They come out of at the highest temperature, usually deepest in the earth. Then your, they don't have the same names here, but the biotite is here. Goodness gracious. I'm going blank on the name now. They use the term pyroxenes and amphiboles. That's true, but we use different names for hornblende and going blank on the other. Okay, but those are the ones that form first. Okay, that come out of solution first at very high temperatures. Okay, very high iron content, very high density. Okay, come this way, less iron, lower density, lighter colors. That way, darker color, higher density, more iron content. So on this side, low density, light colors. Granite is the most common example. Formed now. Granite does have coarse grains, crystal size, so therefore it's intrusive. But it was near the surface, but it cooled slowly, making the large grain. Okay. Now, if it was right near the surface and cooled very quickly, small grain, that's what we call rhyolite. Okay. These are rocks. They're not minerals. They're rocks. Okay. What minerals are contained? The closer to the surface and that you get, more quartz. Okay. You have your potassium feldspars, which are also called orthoclase, and then your sodium-rich plagioclases down here, and then the calcium-rich plagioclases down here. These are your feldspars. This is potassium, sodium, calcium feldspar. Okay, these two are called orthoclase, these are called plagioclase. Okay. Now you get these mixes of it. Near the surface, even the granite, have biotite in it. That was a little black speck you saw there. And most granite will have some of that. Some is very light colored granite, some is, a little bit darker. You have the brownish granite, and we'll see some examples of that, without much white or very light color at all. Okay? So all those can be classified granites. Okay. Now, those with high ferromagnesium composition, there's always some in it, but high ferromagnesium composition, because there's more iron, greater density. Because there's more iron, darker color. Okay? And as you go that way, you get into your basalts. Okay? Now, when we were redoing our master bathroom at home, it's not a huge bathroom, it's small. Our house was built in the 1930s, so they didn't waste a lot of time on big, luxurious bathrooms. Sort of a small room. But whoever put it in, they did it cheaply. It was done after the house was built, okay? And it had a, I'm hard pressed to remember exactly what the floor did look like. It was just sort of an innocuous kind of floor, and just the standard little, and it was sort of a ugly pinkish kind of towel for the shower and stuff. And we didn't mind it too much. My wife wasn't a huge fan of it, but she didn't mind it too much. But we kept getting mold in the ground. And we could wash and clean and everything, and it was still black. We could not get that out, and we didn't know what was going on. Finally, we were working at it so much, we were beginning to lose some of the grout, and it was still black. It was still, mildew in it. And she finally said, "Look, I give up. Let's have this bathroom redone." So we brought in this guy. When we bought our house, the realtor, it was a couple, and they were really nice folks, and he knew his stuff, and he knew good quality people. And we didn't like the carpet that was in the den, and we want a towel there. So he said, "I've got a good guy. If we can get him, he's a good towel guy." And we got him, Lonnie Palmer. Really good at what he did, and really reasonable too, but really good. Gave us good advice. He, when Karen wanted something, he said, "If you do this, you're going to have this problem." Sure enough, he was just right. So we did it his way, and he did a great job. Well, so it came time to redo the upstairs bathroom, which we were tired of toweling. Let's see if we can find Lonnie again. Luckily, we found him. Okay, and he did it in between other jobs. He was working full time for someone, and coming on evenings and weekends, and he did a great job with it. We had picked out just some simple things, sort of some whitish kind of towel for the floor, sort of a tannish for here, a border, and stuff. He said, "Oh, you need a little," and another for the shower floor, which is a little bit different. He said, you need a little more contrast here. Go find me some black granite." Black granite. He said, "Yeah, just go ask anywhere." So I called around, looked around. "Oh, yeah, we got some." So I went and got several things of black granite. He did a great job. The whitish kind of floor, he put a pattern around and put little squares in between. Just did a great job. Didn't charge us a penny more. He was an artist. He was a craftsman. He just enjoyed doing a good job. And he did some other things with the border and for the recess. It just did a great job. Well, later I was talking with my niece, who was a geography major. She had gotten her master's in that at Eastern Kentucky University. Later, she went into climatology at South Carolina, but this was right after while she was doing that, her geology type thing. And she said something about it. I said, "Yeah, he had me get some black granite to put in here." She said, "Black granite? There's no such thing as black granite." Now, this is before I ever taught this course. I said, "Well, that's what he called it. Well, there's no such thing as black granite." She really know-it-all kind of thing. No such thing as black granite. Okay. Well, later when I taught this course, I said, that was basalt. It's not granite. Granite's over here. Granite's always light colored. So therefore, black granite is a contradiction in terms. You cannot have black granite. Okay? I have some samples of this you'll see later. Okay? When we do the lab for this chapter. Basalt is very fine grained. You'll look at this and you see very small crystal sizes. Basalt. And that's their example here. Very dark colored, black. Okay? Now, when we had built the house over on the farm, just a little 2-bedroom bungalow, just so we'll have a place to stay when we have to go to the farm. The countertop, they just happened to have a piece around. Karen liked it, chose it when I didn't know what it was and put it in. It's dark, black, just like the tile in our house here in the master bathroom, but it was large crystal size. Gabbro. And later when that know-it-all niece came, she said, "Oh, nice piece of Gabbro." I got that right. Okay. So, but she was absolutely right. There's no such thing as black granite. That's basalt or something else. Granite, by definition, is light colored. Light in color, low distance. Low iron content. Basalt, anything dark, almost guaranteed to have high iron content. Couldn't be black granite. And it wasn't. It was basalt. Okay. So there's that. Way more than you probably wanted to hear. All right. Now, in your book, there is a blow-up picture of granite, like we had the picture of granite here. In your book, they show a blown-up picture, and it shows the grains of biotite and probably the feldspars in here, and then the light-colored crystals, which are probably your quartzy-type crystals. Okay? Mostly light. Certainly it has some dark in it, but it's mostly light. But you see here, even the lightest of your granites has a little bit of biotite in it. This won't have much. Over here you have much more. Here you have more, about 30% is biotite. It's still granite. Okay. All right. That was igneous rock. Now, before we move on, for some reason they stuck it in here. I guess it's as good a place as any. I would have put it earlier in the chapter, though. The cost of mining mineral resources. Actually, the cost is mostly in the mining. Now, if they're very valuable resources, then someone else jacks up the price because of that. But the cost of mining them, most of the time, it's in that. Well worth a read. Science and Society, more than half a page there. Okay. I'm pretty sure that the example 17.3 is referring back to this figure we just had here. It's in your book, and that's sort of fun to go through and estimate and see what kind of materials you think you may have there. Okay. So let's move on to sedimentary rock. Okay? What made igneous rock igneous rock? Formed from molten magma and or lava. Okay? Sedimentary rock, on the other hand, and we're going to talk about in the 2 chapters from now how rocks disintegrate, how they deteriorate, how they break apart. Well, when they break apart, they form particles. Now, the particles may get washed all in one place and put down in a layer, and then layers on that, and layers on that, and after a while, you got lots and lots of layers, and that forms new rock. That's sedimentary rock. And it doesn't have to just be particles. It could be dissolved materials. So we basically, right here, 2 classifications of sedimentary rock. We haven't gotten there yet, but you just see it here. Made from particles or made from dissolved materials. So we'll get there. But they're all from previously existing rocks. Now, what could those rocks have been? They could have been igneous rock. They could have been other sedimentary rock. Or they could have been metamorphic rock that weathered away and solidified and became sedimentary. Maybe again. So let's look at the sediments. What are we talking about? Well, the sediments could be, if they're going to say this, they should say accumulations of clays, silts, sands, or other materials that settle out of water. That's what we mean sediments. Okay? Now, I put a clay in there because you have some rocks that are formed from clays, not silts. And why I put it there at the beginning rather than at the end is that clays are the very tiniest particles, the incredibly tiny particles. To be a clay, let's see if I've got a dime. There, I have a dime. This dime is about 1 millimeter thick. Okay? If you were to take this dime, theoretically, and slice it into 1,000 equal slices, theoretically, okay? If you could do that, then 2 of those slices together, that thickness, that would be something you could probably see through, okay? 2 of those slices would be the maximum size of a clay particle. You can't see a clay particle with a normal microscope. You have to have an electron microscope And with electron microscopes, some clay particles so small you can't even see them clearly there. They are incredibly small particles, okay? But they still have crystal structure and everything else. That's why I say clay particles were formed by other materials coming back together and recrystallizing. So, making the tiny little clay particles are silt particles, which go from 2 microns, 2 slices of that, up to close to 2 dimes put together. Close to that, no, not really too close to that. Sand would be up to 2 dimes put together. That would be a sand size. Or other materials. Well, what other materials are we talking about? Gravel, big chunks of things. You can have rock made out of that. Sedimented out of water. It was carried along, settled out, got buried and got buried and got buried. Pressure, temperature, reformed it into a new rock. That's sedimentary rock. These are called clastic sediments, accumulated from rocks at various stages of breaking down. These are actually physical chunks, particles, clastic sediments. That's one type of sedimentary rock made from clastic sediments. Okay? So we're looking at the top part of this table now. The biggest pieces of this would be called, in the classic sediments, the sediments of particles were larger than sand size. And again, sand size is the size of 2 dimes put together. I don't have 2 dimes, so I'll use a dime and a nickel. That's the maximum dimension of a sand particle. Anything bigger than that, that's going to be called conglomerate or breccia. Or it could be breccia. I don't know how to pronounce that. All right, now, what makes up those? We'll see that in a later slide, is the appearance of those large particles. This could be chunks of gravel or things like that. Okay, if they're angular, they're one kind. If they're smooth, they're the other. We'll see that a little bit later. Okay? Now, if the particles that go up to make sedimentary rock are sand size, then you get sandstone. And we'll have several examples of that during the next lab. I've got several that I collected at various places, and others have been given to me. Then the smaller, the silt size or clay size, and here's the difference between a silt and in fact, these 3 here. These are soil classifications: sand, silt, and clay. Sand is anything that's rough. When you feel it, rub it between your fingers, you feel the grit in it. That's sand. Less than 2 millimeters. Okay? Now, silts would be like flour. Very, very fine, but no grittiness to it at all. You know, like flour when you make bread. You can also, I've heard them called dust. Okay? No grittiness to it. Clay, submicroscopic. Less than 2 microns. Very, very, very small. So what are the rocks formed out of these? Siltstones, clay stones, or shale. These are the sedimentary rocks out of that. Now what's the difference between these? Siltstone and claystone would be rocks made out of this. And this could be some of those rounded things there because you can't feel much grittiness to them on some of those. Okay? The shale, however, is always in layers. Okay? But still no grittiness to it. That's shale. Now we'll get to this part later, so I'm not going to go over it now because we don't have the slide yet. You're going to see this like 2 or 3 times, okay? So don't sweat, we'll be back to it. All right? So let's look at these clastic sediments. A little bit bigger, okay? If it's bigger than 10 inches, that's called a boulder. Okay? All right. I don't think they make many rocks out of boulders, okay? They're rocks themselves. Gravel would be anything between a small fraction of an inch to 10 inches. That's this. Now here's where we get your definition here, conglomerate and breccia, so you didn't have to memorize it. Conglomerate is a rounded fragment, so the gravel that you have in there is sort of rounded, sort of like that river rock. Breccia has angle. You have distinct angles in there. And we'll see, I think, some pictures of that a little bit later. Okay? Then sand, anything from pretty small to 2 millimeters. That's 2 dimes together. That's going to be sandstone. Silt, and they call it dust here. I would say flour would be the better term. Very slick. This would be siltstone. And then clay or dust, that's not a very good term. Submicroscopic. I mean, less than 1/1500 thousandths of an inch. I mean, that's so small. It's a dime sliced 1,000 times. 2 of those together. Okay? Those are called claystone. Now, both of those are sometimes called mudstone. They're called shale if it splits along parallel planes. Okay? So, and I've never actually seen this described before, but I've read about and actually have touched before a type of material they call soapstone. Soapstone is so slick feeling, there's no grittiness there. I think that must be claystone to be that slick. It could, I guess, be siltstone, but there's not much difference between them at all. Okay. So those are your clastic, made out of particles, broken pieces of rock. Okay? Then the second classification of sedimentary rock, besides clastic sediments, are chemical sediments. And as the name implies, these are formed from dissolved rock materials. And most of the time when they say dissolved, that means dissolved in water. Yes, in rare occasions, it can be dissolved in other stuff, but usually water. There's 3 of the sedimentary paths. Okay? Now, trying to think of an example that you may have seen before, and you probably haven't seen this before, but I remember the very first chemistry lab I did when I took freshman chemistry at Georgia Tech. The very first lab we did, we had some silver nitrate dissolved in water. That's about the only chemical form of silver that is soluble, silver nitrate. Okay, you couldn't see it, it was just dissolved in water. Okay, and we dropped a few drops of calcium chloride into that. So that's just a salt, not sodium chloride, but calcium chloride. Immediately we saw something come out. And by the way, calcium chloride was a clear liquid too. So you had a clear liquid, you dropped clear liquid into it, and suddenly you saw a cloud come out and settle at the bottom. That's called chemical precipitation. Precipitation isn't just rainfall. It's anything that falls. Goes down a precipice, precipitates, okay? And if it's a chemical precipitation, you have something in solution, it interacts with something else in solution, and no longer is in solution but comes out of solution. Okay? A lot of solutions are like that. Okay. This happens deep in the ocean. You may have very low concentrations of calcium chloride calcium carbonate in solution in the water. But your temperatures get really low and some of it starts coming out. That is chemical precipitation. That's a chemical sedimentary rock. It was in solution, it came out of solution, and hardened and became that. Okay, another form we talked about, the pot of salt water on the stove, you forgot to put the beans in, it evaporated. That crystallization from evaporating water. Okay? Don't know if you've ever been to the Great Salt Lake. I haven't flown over it. I've heard it said about the Dead Sea too, probably Death Valley in California as well. Water comes in, evaporates, and there's no runoff anywhere because Death Valley and the Dead Sea, they're as low as you can go. Those are the 2 lowest points on the surface of the earth. They're below sea level. Water flows in, but doesn't flow out. And therefore, where it loses its water, it's going to evaporate. All that water flowing in has dissolved material in it. It keeps on getting this dissolved material, They say on the Dead Sea, it's almost impossible to drown. You have to actually almost hold someone upside down to get them to drown. Because if you were to get on the Dead Sea, you're going to float like a bottle. Okay? Because there's so much salt in the solution. Salt water, you float easier than fresh water. I don't know if you've noticed that before, but you do. The Dead Sea is really dense. Well, the sands around there, that's why it's called the Dead Sea. All those salts have come out of solution. Death Valley, same thing. Nothing much will grow there. Salt Lake City, Salt Lake, the Great Salt Lake, was a body of water, and then it's evaporated, leaving the salts there. Very, very high salt content. So, what's that?
I know about that. But when you say like below sea level, like I know Louisiana is below sea level.
Okay.
So and
Not all of it, but part of it.
Yeah, part of it. And I also heard that eventually it's not going to be like they're going to be in the ocean.
Yeah.
So how does it work? I'm confused. Like,
Okay. My brother lived in New Orleans. Now, that's about the only part that's below sea level is in New Orleans. What they have are the big, what's the term? Levees. The big levees around keeping the sea out. And what had happened, that it was dry land, it was marshy land. And they drained the marshes and stuff, and it was right around sea level. But as long as it was marshy, a lot of the water occupied the spaces between the soil particles. When they drained it, then it collapsed to a certain amount. Also, it had lots of organic matter because everything is washed down in the marshy area. And the organic matter dried up and evaporated basically away or oxidized away. So it just kept sinking. But they had all the levees around that allowed them to do that. So actually it keeps sinking in many ways. Okay, and that's why it's below sea level. Now, sure enough, if global warming continues unabated, and we keep losing more and more of our polar ice caps and glaciers, we'll talk about this in later chapters, sea levels are going to continue to rise. And as they rise, they either got to build taller and taller levees, or else water's going to creep in. Huh? It'll just get below water. It won't be dry land anymore. It will have to be either back to being a marshy land or actually go back below water. Now, there's some places people have done that intentionally. The Netherlands. Large areas of the Netherlands, they built the dikes and the dams and various things around there and pumped the water out. That's why the big windmills, and they are below sea level too. City in Italy, Venice, has very few streets because it's all a series of islands, and people built on those islands. But as the sea level has risen, most of those people, if they had first floors, they're now basements, swimming pools. No, yeah, but they're actually below water now. So as the sea levels rise, which they are doing, there are some of the coastal towns in Florida are either below water now or they're having to build levees and pump water out constantly. So it's just going to keep happening. And there are islands out in the Pacific, low islands that are losing more and more land. And in a few years, they're not going to be islands anymore. They're going to be underwater. Okay. So yeah, it is happening all over the globe, So I think that's going to happen in New Orleans too. Either they're going to have to keep building taller levees, or they are going to have to let some of it go back to being underwater again. I assume the Netherlands have invested so much in theirs, they're going to keep building levees, but I don't know.
So that it makes them like prone to like flooding.
Yeah, and boy, if you have things like happen in Houston, those are above sea level, but they're very flat. There's still areas, I think, that are below water, and probably still houses with waters in the basements and things like that, because there's just nowhere for the water to go. South Florida is going to maybe experience that very soon. When is it supposed to land? The weekend?
This weekend, Sunday.
Yeah. And who knows, that's more powerful than Harvey was. Now, whether it's a slow moving, see, Harvey, this problem was so slow moving, it just dumped and dumped and dumped in the same area. And then it decided to turn around and come back and dump some more, you know. So it was the worst possible situation. If Irma, is that it? Yeah. If she moves quickly, she'll dump a lot of water, but move on and dump it somewhere else. And so far, it seems to be moving. It's not getting stationary. But once it hits land, it tends to slow down.
But it's 2 more behind it.
Yeah, and then there's 2 more coming behind that. So, yep, this is it. Yeah. And actually, we're a little late for it, but we've had some of our worst ones about this time of year. Okay. So that's the second time. We have precipitation from chemicals coming out of solution when the conditions, either the concentration gets too high, the temperature drops, something like that. Crystallization from water evaporating away, or biological sediments. And that's sort of what we were talking about before. In the swampy, marshy areas, you have really thick organic things like peat and stuff like that. And those are biological sediments. And as they continue to build and things form on top of that, that's where coal comes from, which I guess you could count a mineral. Now, the problem with that is, remember we said a mineral, by definition, was inorganic, not directly from living things. But see, coal has been so long since it was a living thing, I guess it could be counted as a thing. But they could be rocks and still be biological. Okay? So here are our chemical sediments. We've already done the plastic before. Here are the chemicals. Calcite, which is calcium carbonate. The rock is called limestone. The mineral is calcite. Now we'll see, I've got some examples of calcite. You'll see those crystals. Very beautiful crystals. But then they're very fine crystals coming out of a solution forming limestone. Now in limestone, you typically have more than pure calcite. You'll have some sand in there, that's quartz. You'll have maybe some shells in there. That would be biological stuff. Quite often with limestone, you'll see little pieces of shell. We'll have a picture of it in the book for that. Another form of chemical is dolomite, which is another form of limestone, but it's called dolomitic limestone. This is calcium carbonate. This is calcium and magnesium carbonate. Okay? As if we hadn't talked enough about those. Another chemical sedimentary rock would be gypsum. We talked about this as if it was a mineral, and it is. The primary mineral is that, but we also call it rock, which has other things in it, gypsum as well. Okay? And then another chemical sedimentary rock would be halite, which is sodium chloride. That's the salt that comes out of solution in the ocean, not the salt that we make or grind or whatever. This is where we got that. Most of the time, that's not purely white. If it's pure sodium chloride, it would be, but if it has other biological things in it, it'll be, in fact, quite often, it'll be a pinkish color or almost a little brownish color. I'm not absolutely certain, but I wouldn't be surprised if that's not what they call rock salt. Have you ever used that for making ice cream and stuff like that? Notice at the end of that, you have some gritty type stuff in there. It has other stuff other than pure halite in it. It also has some quartz and other things there. Okay. So here are some pictures of some of these sedimentary rocks. This is actually a piece of limestone. We'll see some others in the lab next time. It's a sedimentary rock. What kind of sedimentary rock? What are the 2 kinds of sedimentary rocks? No, those are igneous.
Oh, that's igneous. That's the sedimentary.
Plastic.
Plastic or chemical, which is limestone. Chemical.
There's one up.
Yeah, it's one up. 50-50 chance here. Okay. All right. This is rock that formed underwater as things came out of solution. Sometimes the remains of marine organisms You see that little piece of shell there? That's biologic. That's not a mineral. That's a biological piece of thing. Okay? They call that a brachiopod, meaning a plant shell, I think. Okay? This is obviously sedimentary rock. At one point, those were horizontal layers, but anytime you see the layering, sedimentary rock. That happens to be sandstone. The reason it's sandstone is a porous structure. Any sandstone, you can feel the grittiness in it. Okay? And the sand grains are there, and it's sedimented out at different times, so you have different amounts of iron or other minerals in there, but it forms a sedimentary rock. The iron oxide bonding, this is from Tasmania, Australia. Okay? Now this is a piece of, this is gravel that made this. So that wouldn't be sandstone, that would be breccia. Breccia because these are angled pieces. If they had been rounded, smooth pieces, that would be conglomerate, but this is a piece of breccia, or breccia. Sedimentary rock. What kind of sedimentary rock? Second? Yeah, clastic. But sandstone and breccia are clastic, actually made out of particles. You can see the particles there. You can imagine the particles there. This was chemical. Okay? Because of the large angular pieces there, that's breccia rather than conglomerate. That happens to be from Colorado. That is, I don't know why they tell you that, but it is. Good deal. And here's that picture again. I said you'd see it several times. I can't think of any reason it shows up here, except they just had room to put it. This is chemical, limestone. Now that right there is not chemical, that's just something that's built into it. But remember, the rock is a combination of many kinds of minerals and other stuff, like seashells, okay? This is sandstone, okay? Now, there probably is some clay or silt in there too, but it's predominantly sandstone. You can tell that was sedimentary because of the layering. Something has bent those layers, but at one time those were all pretty flat. And this obviously is plastic because you can see the chunks of angled gravel that is in there. Now, what in the world could have formed that? Here's my guess. Colorado, glaciation. Probably a glacier brought all that stuff down. The pressure of the glacier cemented it together and formed this breccia. You can't pry those things out. That's all in one rock, but you have all those little pieces of rock that are in that rock. Same thing with the sandstone, you just don't see the little pieces. Okay. In your book, you have a piece of breccia. I guess both of those are breccia. Okay? And again, they're from Colorado, so I'm guessing glaciation. You can see a piece of sandstone, similar to this one, but it's a more horizontal layers. And you see some limestone, sedimentary rock that formed underwater. Those look like layers that you would expect in plastic rock, but you also have layers of limestone. And frankly, when you drive from here to Huntsville, and you see the road cuts, and you see the rock on the side, most of the time, in fact, not just there, just about anywhere, when you see those road cuts and you see the original rock there, a lot of times that's going to be limestone, okay? And you'll see some of it looks very similar to that. What's that?
Could you take it and sell it?
You could, maybe, but it's pretty cheap. Probably not worth your cost of getting it up. Now, there is a closer look. And this is focusing on asbestos. Pretty bad word, right? Now, y'all probably are not old enough to remember, but I remember when asbestos was a new wonder material. What made it so good? It will not burn. It is totally inflammable. So good stuff to make insulation, good stuff to make building materials from, because it won't burn. You can't have a fire with it, you know. Fantastic material. In fact, I can't remember when it was, several years ago, somebody, my father-in-law or a brother-in-law or sister-in-law, somebody had gotten some old television shows. The one I remember was George and Gracie. I don't know if you remember, George Allen and Gracie Burns. They were a married couple. They had been on vaudeville, and then they made it in the early years of television. Really funny couple. One of my favorites when I was a kid growing up. It was old back then, but you know. They had the show, and then they had the commercials in between. And the commercial in between was bragging about this asbestos tile. The tile to put down in your floor, because it will not burn. It's great looking, it's durable, it's all these things, and it will not burn. And of course, a few decades later, they found out people who mined asbestos were getting very, very, very sick. It's not black lung disease, but asbestosis. Yeah, just all sorts of lung problems. Because those little particles of, and it's a clay, little particles of that, little fibers got into the lungs. You could not clear them out. Caused emphysema, caused cancers, caused all sorts of problems. But guess what? Not all asbestos causes that. But if it's called asbestos, people stay away from it. But some asbestos does not cause that at all.
Going to tear down some old building.
That's it, exactly. Because they think there's asbestos in it. In order to tear them down, you have to have a hazmat, be all suited up, and ventilation and trapping the stuff that blows out. You can't allow people to breathe that. It's a little bit of overkill, but for safety, I think it's worth it. But when you read this article here, you'll find out there's an awful lot of really good asbestos out there that doesn't cause any of that. We could be using, but because people don't distinguish, if they see the word asbestos, no way, they're not going to get close to it. All right, now, let's go to how these sedimentary rocks form. We know what they form of, either chemical or clastic sediments, but how do they form? Okay? This is called lithification. Okay? When you see lith as a prefix or suffix or anywhere in a word as a root, you know it has to do with rocks. Okay? Just know that. So this is how the rocks are formed. And we're talking about sedimentary rocks. So this is the rock forming process for sedimentary rocks. We know how igneous rocks are formed. Magma cools and solidifies. Okay? But how sedimentary rocks are formed, again, two main parts. The first part of this is compaction. Remember I said all along, sediments come out of solution, out of water, and they settle. But then you get other sediments on top of them, on top of them, on top of them, and finally somewhere down there you have, way deep, you have compaction. Because all this weight of everything else is on top of it. If it compacts, it's squeezing the particles or chemicals closer and closer together, squeezing out the water. Okay? Anytime you have, okay, here's a dumb question. Would you say a soil is solid, liquids, or gas? Solid. Okay? It's not. A good, productive soil is about 50% solid and 50% pore space. Because guess what? Roots need places to grow. So if it's totally solid, there's no place for roots to grow. To be a good, productive soil has to be 50% solid and 50% pore space. Now that pore space, to be a good, productive soil, needs to be about 50% filled with water and 50% filled with air, because plants need water to live, but they also need air to breathe. So a good soil is all of the above, solid, liquid, and gas. Well, when you have sediments going in there, they start out with a lot of pore space. And then as it gets squished more and more, the pore space gets packed out of it, and what mostly is in that pore space is water, squeezing out most of the water. Okay? So that's the first part, compaction. You've got to get that water out of there before it can become a rock. The second part is cementation. Those particles have to get joined together, cemented together. So the spaces that are left between the particles now need to be filled with some type of a chemical deposit that actually binds them together. And guess what? As the water gets squeezed out, mostly the pure water comes out, but the other stuff that was in the water, like dissolved in the water, that may stay and hang around. That would be the stuff that cements them together. So the chemical deposit binds the particles together. That's the cementation. If you don't have enough compaction, you're not going to form a rock. If you don't have adequate cementation, you will not form a rock. You'll form particles, okay? So you need both of these parts, compaction and cementation. And the figure in your book shows this. Here is the original deposit, about 50% particles and 50% pore spaces, okay? Different particles here. I think they've got it mislabeled. The white one should be the quartz. The pink could be the feldspars. I don't know what the dark ones are. But they're just different minerals that make up these particles. Okay? Then the overburden, more stuff gets packed on top, and these pieces get pushed more and more together. That's the compaction part. Okay, you still have little pores in there, but not nearly as big as they were a while ago. Well, then you get something, either what was residual from the water or something that comes in later that is your cementing agent, and that sort of sticks them together. Yeah, they call that the cement. The stuff, the goo, whatever it is, yes.
Liquefaction.
Right.
Lithium also has something to do with the lithium, the drug?
No, actually, even though that looks like it's the same thing, it has nothing to do with lithium. Another word that I thought this is what you were going to ask, lithograph. I don't even remember exactly what that is, but that has nothing to do with this either. This is lith from rock. Okay, I'm not sure what lithograph is. Maybe that comes from rock too. I don't know. This is from rock, so that's what it means. Lithium is an element, but I don't think it has anything to do with this. It's fairly rare. You don't see a lot of that. Actually, batteries nowadays are using more and more lithium in them. It's not that common, so that's why batteries are pretty expensive. Okay? But then when you have the compaction and the cementation, now that holds together. Now you got a new rock, and that's a sedimentary rock. Okay. I think that's the last of sedimentary. Now, before we get into metamorphic, there's another Science and Society blurb here that's using mineral resources. Earlier we had the cost of mining mineral resources. Now we have using mineral resources. It's a nice little blurb. Talks a lot about that thing about phosphates and how rare that's coming and how in the world we're going. Oh, let me get back on that a little bit. Because of the Haber process, suddenly we got to be able to produce all the nitrogen plants could use. So no longer was nitrogen our limiting factor in plant growth. That really spawned the Green Revolution. Now we could grow, it seemed like, as much as we want. Problem here, we're using up most of our phosphate. You can't make phosphorus from, there's no phosphorus in the air. There's no, like nitrogen's in the air. That's where you can make the nitrogen. You can't do that, okay? So where are we going to get new phosphorus sources? They're very expensive, very hard to do, deeper and deeper, rarer and rarer. We may soon not be able to feed our planet just because we don't have enough phosphorus source. Let me give you a little bit of a bright side to that. There's lots of phosphorus out there, okay? Most of it is just not usable by plants, okay? Plants can't get to it because it's really tightly bound. But I have a friend who actually, he's a veterinarian, but he's a missionary in Cameroon, a small country near the Congo, okay, Central Africa, fairly near the equator. He told me about a plant that grows wild there that is a bush, but what they found out about the bush, that plant is a fantastic miner of phosphorus. So basically what we may get to doing in the future is everybody planting this bush is not very pretty, not attractive, it's not usable for anything except grind up that plant material and then spread it over your plants. That's good usable phosphorus. It takes non-usable phosphorus, it mines it somehow, gets it into its material, and then do that. And by the way, one good source of phosphorus is mulch, because plant material contains phosphorus, so the more you mulch around your plants in your yard and that kind of stuff, you're probably going to wind up with enough phosphorus that way without having to add that much for a fertilizer. But the fertilizer phosphorus getting very expensive. Commercial agriculture, they don't mess around with mulching, they don't mess around with grinding up bushes, they want a chemical to put on it. I don't know how they're going to get it. Okay, before we get to metamorphic rock, there is a thing here, people behind the science, and before I read this book, I'd never heard of this guy. Victor Moritz Goldschmidt, okay? Swiss-born, Norwegian, okay? Born in Switzerland but grew up in Norway, and I think at some point he may have even come to the U.S., but he's not considered American. But anyway, he did a lot of the early work in mineral chemistry, that kind of stuff. So I'll let you do that. But as you read this article, you'll find lots of other names. Josiah Gibbs, Lawrence Bragg, William and Lawrence Bragg, Max von Laue, so you can find out with lots and lots of other names if you read this. Now remember, if you choose to write on this guy or any of the others, this is not your source. You have to get outside the book to find sources, not the book itself. Okay, enough of that. Let's go on to metamorphic rock. What are the other two types of rocks? Second? I can't hear well. Sedimentary and igneous, right. Metamorphic. What in the world is metamorphic rocks? Well, metamorphic rocks were previously other kinds of rocks. They could have been igneous. They could have been sedimentary. Or they could have been other metamorphic rocks. But they've been changed. Remember we talked about the altering with heat, pressure, and hot solutions? These are rocks that have been changed by heat, pressure, hot solutions into distinctly different rock. Chemically they're the same pretty much, but mineral-wise, how they're put together, totally different. Okay? Now, the key here is the word change. Metamorphosis. What is an example of metamorphosis? Butterfly. It was a fuzzy little ugly caterpillar, became a beautiful butterfly. Same thing. Same living organism. It changed big time. You couldn't even recognize it from its previous state. Metamorphosis. Now, I can't think of the guy's name. He was a weird German writer, I think. But he wrote the story of the cockroach. It's this man that was really gripey, obnoxious and stuff like this. He woke up one morning, he had been metamorphosized into a cockroach. That was supposed to mean something, but metamorphosis, total change.
Do you count those with tadpoles and frogs?
Second?
Do you count those with frogs?
A tadpole and frog is probably pretty close to metamorphosis. I don't know if they actually count that, but it sure sounds like it to me. Okay? So I wouldn't be surprised if that's another point. For any of you who might be biblical scholars, Romans 12:1 and 2 says, don't be conformed by the thing of the world, but be transformed. That word was metamorphosized. Completely changed by renewing of your mind. If you're into that, that's metamorphosis. Okay? Complete change. Okay? Causes of this. They're often associated with geologic events, as in, if you notice here, heat, pressure, hot solutions. That could be volcanic activity. That could be plate tectonics, movement of the crust, heating in solutions from magma intrusion. Temperatures must be high enough to cause recrystallization, but not melting. If you add heat and add heat and add heat, as long as it stays a solid, you can change the crystal structure. That's metamorphosis. You add more heat, you can change it again. But add more heat, at some point you're going to melt it. Once it melts and re-solidifies, what's it now? What rock comes from magma? Igneous rock. Okay, it's now no longer metamorphic, it's now back to igneous. Okay? So here's a graph that shows a few of these. You remember shale? We mentioned shale. What kind of rock is shale? It's on that table we saw 3 times.
Plastic?
It's a plastic. What kind of plastic? What type of rock? Sedimentary. Plastic sedimentary rock, and the material was silt or clay. Silt or clay. In layers. Okay? All right. Sedimentary rock. With more heat and temperature that metamorphosizes, this is sedimentary, metamorphosizes into slate. Anyone have any familiarity with slate?
Yeah.
Really?
Yeah.
Okay.
Isn't it the ice that covers the gravel roads during storms? The slate?
I'm not sure. That may be. I was thinking more roof tiles. Some of the old buildings, for instance, New Orleans was almost completely wiped out by a fire early in its deal because roofs caught on fire. And they just jumped from house to houses, because they had, I don't know, I think they used cedar shakes or something like that. Once they dropped, they burned like crazy. They're good kindling. Okay, so they quit using that and brought down, I think, from Pennsylvania, slate, and they did all the roofs in slate. They don't do that anymore much. But our church in the south side of Birmingham, part of the oldest building has slate roofs. Very expensive to repair, but they last a long time. Chewy Tootsie Roll. But if you keep adding more heat and temperature to slate, it metamorphosizes again into schist. Okay? Now schist is yet a harder, different chemical composition again, same, but the mineral composition, you've changed the bonding, chemical bonding that you have. Well, you add more heat, add more pressure, and you get a nice rock. No, it's nice. The G is silent, okay? Remember that one at the beginning that said one of the oldest rock, and it had all that been? That's from all that heat and pressure, changing it around. That was a piece of nice. That's a hard rock. It's been metamorphosized 3 times from shale, which was sedimentary, to metamorphic slate, to another metamorphic schist, finally to metamorphic gneiss. Add more heat, and what happens? It melts. And when it re-solidifies, now it's granite, which is igneous rock. Granite is igneous rock. Once it melts, it goes back to being igneous again. Okay? As long as you add that heat and pressure without melting, then you keep making it metamorphic. Now, remember that limestone? Most of Alabama is underlain by limestone. It's a fairly soft rock. What kind of rock is it? Which of the three? Second? It's a chemical of what? Sedimentary. Chemical sedimentary rock. It's pretty soft. You know, some of it you can actually almost scratch. But if you put that under like great temperatures and pressure, it changes to marble. Beautiful, one of my favorite rocks, okay? Much harder than limestone. Much more durable than limestone. Only problem, two problems with marble. One, it fractures real easy. It chips easily if you hit it just wrong. The other thing is, because it came from limestone, which is calcium carbonate, still has calcium carbonate in it, just recrystallized differently. But if you get much acid on it, you etch it really easily. And the old marble will no longer have a shiny surface. It'll start getting, but it's still pretty, I think, pretty. When we redid our kitchen, my wife wanted marble countertops. I couldn't have been more pleased. I love marble. Okay. They were expensive. She paid for them, so I never knew how expensive I would have on the granite, right? But we got marble. But we have to be very careful not to let any vinegar, actually coffee, anything that's sort of acidic, tomato juice, you know, get it up right off of there as soon as possible.
In that marble or granite they give off a gas, one of the countertops.
I guess any of
it that could be, that in time could be dangerous.
Okay. I'm guessing what gas it would give off would be radon gas. And that could be just about anything, probably more likely granite. It would just have to have trace amounts of uranium or radium in it, and it does give off gas.
Some people have opted to get imitation. I guess if it's granite, imitation granite top,
right,
rather than real deal. I mean, obviously it's probably cheaper, but they said because of the gas it gives off.
Well, actually, there was a company, I'm pretty sure they're out of business now. They were making sheetrock, gypsum board. When they were manufacturing sheetrock, their gypsum, the calcium sulfate, that happens to occur in the proximity of phosphates, which always have little bits of trace amounts of uranium or radium in them. And guess what? It was worse than that. They were going to the mine spores, whatever you call that, after they had extracted the phosphate, so you had built up amounts of uranium, and they were using that to fill in the gypsum board. And they were actually, you could take a Geiger counter and go, you know, and there was sheetrock made out of that stuff. And that certainly could give off radon, okay? And maybe just radiation itself. So yeah, it can happen with any naturally occurring material. I think part of what you're saying too, they are making more of a quartzy type countertop out of sand. And actually, I've seen this, and it's really pretty, using old glass and pressing that and actually doing the same thing that lithification is, compaction and cementation and forming an artificial. It's not a naturally occurring rock, but they can be really, really pretty. Very hard and not giving off anything.
I'll just say it's after 5.
It's after 5, okay? At 5:15, so we got 6 minutes. Okay, 6 minutes. I don't want to cheat you out of a penny of your tuition dollars. Oh, I can hear you now, running to the dean saying, he cheated me out of 5 minutes of my tuition dollar. I can hear it now. Okay, let's go real quickly. We'll finish this. Sandstone. What kind of rock is sandstone? Sandstone?
Whatever sand is.
Clastic sedimentary rock. Add heat and pressure to that, you get quartzite. Okay? Quartzite is metamorphic rock. It changes the crystal structure. The chemical content is the same, but the crystal structure has been modified. Much harder. Doesn't flick off. You can't rub off the sand. And more heat and pressure, you actually melt it and it goes back to being quartz. What's that? If it came out of melted, igneous. It became igneous again. All right, let's start with a fine-grained igneous rock. Okay? Rhyolite, I think, is a fine-grained igneous rock. You add heat and pressure to that, you might get a schist. Very similar to what you got over here from sedimentary rock. And then you add more heat and temperature to it, heat and pressure to it, you get gneiss, another nice rock. Okay? But then you add more heat, and what happens to it? It melts, goes back to granite, which is igneous rock. Once it melts, it goes back to being an igneous rock when it resolidifies. Before it melts, you're metamorphic. All right. Let's see, where are we? Okay, I think this is the last slide before the rock cycle. So let's hit this one, and then we'll come to the... no. All right. All right, we will classify this next time. Okay? And this will be it'll be the thing that covers foliation. So that's where we'll pick up next time. Good deal. Thank you. All right, let me get this marker back in here. And oh, and by the way, I meant to say this, okay? Remember I said that a lot of Alabama was underlain by limestone. Well, some of that has had a lot of heat and pressure over the years. And do you know what they do down in Sylacauga? They mine marble. In fact, there is a type of marble, this is what we have in our kitchen. It's called the Alabama white. It's some of the whitest, prettiest marble. I think Buckingham Palace ordered some Alabama white marble from Sylacauga when they were doing something in it. It's a very pretty marble, very white. Now, it has still the streaks of other things in it, but the pure parts that are white are some of the whitest, really, really pretty. Sylacauga, Alabama. You'll find some of that. That's where they do some of the mining. Alabama white marble. I wanted to say that. This picture here, they don't say where it came from, but that looks like it could be that. We'll talk about that later. All right, I'm going to, any questions before I shut this down?